morning, Ashutosh ji.
Namaskar, sir. Good morning,
Namaskar.
sir.
Good morning. Good morning, Gautam ji.
I think, sir, there is some problem in the connection.
Okay,
Additional secretary, madam, and data staff is just going to join.
okay. Yeah,
I'm just waiting for them.
no problem.
Thank you, sir. I'm sorry to all. We're just waiting for 2-3 minutes more because so many of the participants and the panelists are not able to join. We're just waiting 5 minutes. Please pardon us.
Good morning, everyone. Am I audible?
Yes, ma'am.
Good morning to all.
I can hear you, Ashutosh.
Yes, ma'am. You are very well audible.
Acha.
I'm participants as well as the panelist. I'm sorry. Yeah. Yes, ma'am.
Matter,
There
I
was some
think we
problem in the technical problem.
can... Okay. So should we start?
Yes, ma'am. Please, we can start, ma'am.
So this is really a proud moment for me to inaugurate this workshop because it has something which is going to train people on a very, very important subject and something which all the legal metrology people are able to at least just one second. So actually, I was trying from another source also so that we can join in a much better position. But since I'm already on a mobile, so I feel that this is something which most of our officers must be trained about, and the uncertainties that are so essential in all the weights and measurement, they need to be need to be taken into account while we are doing the works of calibration, and particularly when we are doing for so many other reference labs. I think most people are actually dependent on the verification and calibration that RRSLs continue to do in our country. And this is what makes the assurance of correctness of weights very, very important in our society, in the progress of our economy. Also, we need to understand that such workshops must be held from time to time because it also gives an opportunity to everybody to upgrade their skills, to understand what are the latest norms, and to also basically apprise themselves of the international standards which are prevailing in the subject. So with these words, I would like Ashutosh ji to carry on this workshop because a lot of people have joined, I can see, and everyone has been waiting for this very, very interesting workshop. Thank you so much.
Thank you very much, ma'am. Your kind words and motivated words are always motivating us for doing something better for the society. And under your guidance and leadership, certainly we are trying our best to do something good for the society. Thank you very much, ma'am. We are always obliged. Thank you, ma'am. Ma'am, we have today with us our topmost beloved National Physical Laboratory Director, Professor Venu Gopal Achanta. He is a well-known scientist in his field, and he is doing very well in National Physical Laboratory. We have visited last time. I think you have not visited, ma'am. And PL under his leadership, I will request you to kindly visit once to the National Physical Laboratory. I'll request our guest of honor, Professor Achanta Saab, to kindly speak 2 words so that we can also understand what best we can do and where are the lackings, where we are, where we can do better. Professor, sir, please.
Thank you, Ashutosh. Thank you, ma'am. You already mentioned the importance of such courses, which we should be having in more numbers. Right. So I'll take a slightly different view, taking what we can do, as Ashutosh mentioned. So we have 4 pillars in the country for to establish and to disseminate or to have the quality infrastructure within the country. Right. These are the NMI, the National Metrology Institute, which maintains the primary standards in the country. if you want traceability, exports or imports, like if you want our measurements, any measurement to be accepted at international levels, so we need traceability. So all our equipment, everything needs to be traced back, calibrated back to the NMI, the primary standards at the NMI, right? And then we have QCI, legal metrology, and BIS. BIS and is formulating the standards. Legal metrology is the most important of these pillars, which is disseminating the standards across the country. And QCI is the accreditation body, which is uh, helping private laboratories to maintain the quality infrastructure within the country. Unless we four of us work together, right? So the quality infrastructure will not improve. The QCI may say that we have increased tenfold, 100-fold, whatever fold they can say, that the number of labs have increased in the country and they're all under the quality infrastructure. But if they're not coming to the NMI for their calibrations and testing, right? So there is no traceability established in the country. Right. So legal metrology, all the labs like so are directly traceable to NMI, and that's one linkage which we should establish and continue to have it. And we should have more such courses between NMI and the legal metrology department so that we can train, we can update ourselves continuously and make sure that the quality infrastructure is propagated across the country. Right. So I congratulate once again Ashutosh and the Legal Metrology Department for organizing this course, and I look forward to having more such interactions in future. Thank you.
Thank you very much, sir. Thank you for your kind words, sir. We are always utilizing your, so we are always using your help or taking your help for making these type of programs. Even I am having with me Dr. Gautam Mandal with us, who is the senior scientist from National Physical Laboratory, and we are taking your help always for the dissemination of technology, knowledge, information in the country. We are always obliged to National Physical Laboratory for maintaining these standards and to disseminate through legal metrology or through the other laboratories in the country. Thank you very much, sir, for your converse, and we will certainly take your help in future courses also. We will request you to kindly come and simply motivate us so that we can do better. Thank you very much, sir. Thank you.
Thank you. Thank you.
Thank you, sir. संतोष जी, डायरेक्टर साहब ने ज्वाइन किया दीक्षित साहब ने?
अभी नहीं सर.
No, sir. Sorry.
अभी नहीं कर पाए सर.
Okay, okay, thank you. So now I think we should start immediately without wasting the time. We are immediately going to the training part of this measurement uncertainty. As we are all aware, uncertainty is in every sphere of life. How uncertain even the life is. So how this uncertainty affects the measurements, how we can go better results, how we can get the better results. We will discuss it with Dr. Mandal. Who will explain us how to calculate, how to measure the uncertainty in measurement of mass and the calibration of balances. Sir, Mandal sir, please. Dr. Gautam Mandal is a known scientist in the National Physical Laboratory who has done a lot of calibration testing. Everybody in the country knows about him, who is working in the field of mass, balance, volume, density, etc. In the country last more than 20 years, and he is helping the society by the way of calibration of weights, balances, and not only in the field of legal metrology but also the pharma field, medical field, etc. So certainly, sir, it will help us to understand how to calculate uncertainty. Over to you, sir, please.
Thank you. Good morning to Additional Secretary Madam. Good morning to Director CS sir, NPL sir, and Director Legal Metrology sir, and Ashutosh sir for giving me opportunity for delivering this lecture. So good morning to all of you, and good morning all the participants as well.
What's going on, right? Mic is there.
So the topic is measurement uncertainty. So now the topic is measurement uncertainty calculation for mass and the balance. So usually we use the term weight. In common sense, we use the weight terminology weight. So by definition, mass and the weight are different, but sometimes we use the same terminology for the this our day-to-day applications also. So what is the difference according to mass and the weight in terms of legal metrology is concerned or metrology is concerned? So I should start from the metrology. What is metrology? So this is basically science of measurement and its application. So there are basically three categories in metrology. One is the scientific metrology, industrial metrology, or the legal metrology. Scientific metrology is basically for the establishment, maintenance, dissemination, all these things, part of the upgradation also. Time to time we can upgrade our measurement system. This is a part of the scientific metrology. And industrial metrology for manufacturing purpose, we provide traceability to the industries, either it is manufacturing industries, process industries, like Maruti Udyog or so. So these are the part of the industrial metrology. And the legal metrology to ensure if one consumer is getting the right quantity. If I am paying 100 rupees for 1 liter petrol, so as a consumer, I have right to get the right quantity. So if we are getting the right quantity or not, to make sure metrology is involved here, because until or unless we measure it, we don't know it is 1 liter or not. Definitely 1 liter is not exactly 1 liter. This should be within the permissible limit according to the YML guidelines. So this legal part is there. Suppose one consumer is being cheated, then legal metrology has authority to take the action accordingly. So this is the part of the legal metrology. So according to SI system, we follow the SI international system of units. According to SI system, there are 7 base units and various derived units. So 7 base units are basically kilogram, meter, second, ampere, Kelvin, mole, and candela. Definitely, most of you are might be aware about that. And from 20th May 2019, all the SI base unit has linked to the physical constant of nature. So today we'll discuss about the kilogram. This is basically realized to the Planck constant. So mass has an application in our day-to-day life. Either we purchase normal grain, vegetables, or jewelry, even for the pharmaceutical industries, even the rocket launching, or everywhere it has application. So that's why we should know the mass with right quantity. So that's why measurement is very important. even few SI derived units like volume, density, pressure, force, fluid flow, and CRM, certified reference material. Those are used, or those are prepared using the gravimetric method, gas metrology, like we take weight of cylinder. So all these derived parameters are established to the kilogram. So kilogram has very important, or mass has very important role even to establish the derived parameters. Even without traceability of mass, it is not possible to establish the derived units. Metrological traceability. This is basically heart of the measurement. So what is the traceability? So this is property of a measurement result, whereby the result can be related to a reference through a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. So basically, this is a property of a measurement results. For example, weighing balance. Sometimes we use the terminology, this balance is calibrated or not. Now, balance is calibrated but not traceable, because using the balance, what we are measuring the mass or weight. So this result should be traceable, and there should be reference to the relate to the reference. So we should have a reference standard which is used. For example, in case of balance, we use standard weight to calibrate the balance, and there should be documented unbroken chain. So we should have documentary evidence that all the measurement results are traceable. Verbal is not acceptable here, so we should have documentary evidence. And measurement uncertainty is very important. Without measurement uncertainty, the certificate is not valid. So basically, there are two parts in case of measurement results are concerned. So measured value plus minus uncertainty. And usually, this is the international practice. Uncertainty is reported at k equal to 2. We talk about the CMCs, calibration and measurement capability. This is nothing but the uncertainty, and all the CMCs are reported at k equal to 2. This is the international practice. So this is the traceability pyramid. So at the top, this is the SI unit, SI base unit, and this is a BIPM. This is basically temple of all the measurement standard. BIPM is the International Bureau of Weights and Measures. This is in France. After that, each and every country, there's a NMI, National Metrology Institute. And this is the government of India has given responsibility to CSIR NPL, and this is our international code NPLI, National Physical Laboratory of India, because there's another NPL, this NPL UK. So that's why our international code is NPLI. So our responsibility is to maintain the national standard at NPL, CSIR NPL, and further we disseminate our standard to the various levels. To the accredited laboratories, then accredited laboratories further provide traceability to the manufacturers, their reference standard, and then the final product is used manufactured at the industries. So these are the uncertainty, and this uncertainty increases with this level goes down, but not necessarily always it will be 10 times. This is only the indicative only. Just I have shown here, this is not necessarily always it will be 10 times. Okay. And not necessarily that NPL will provide traceability to the accredited labs and accredited lab to manufacturer. And even manufacturer directly can get traceability from the NMI also. So there is no hard and fast rule that traceability should be maintained like that. This is depending on the accuracy classes also, and uncertainty they require. They can get calibrated their instrument or reference standard directly from the NMI also, or any other accredited laboratories. So basically, this should be unbroken chain. And this is the hierarchy of mass standard and the traceability. Before redefinition, before 20th May 2019, international prototype of the kilogram, which is kept at BIPM. This is made of platinum iridium, 90% platinum and 10% iridium. This is basically 39 millimeter height and same diameter. This is cylindrical shape weight. This is, density is 21.5 gram per cubic centimeter. This is kept at BIPM. It was used as a international standard. This is a single piece in the world. This is kept at BIPM. And those who are member state of the BIPM has given at least one national prototype of the kilogram. Like India has become member in 1957 after implementation Weights and Measures Act in 1956, and we got this copy number 57. This is a unique number in the world. Anywhere in the world, if you talk about NPK 57, that means this is for India. And being NMI, we maintain the national prototype kilogram. This is NPK 57 at CSR NPL. And every 10 years, we get calibrated from BIPM. And it is due in this year. We'll send it to BIPM for the recalibration. And after that, since this is a national property and this is single piece in our country, so it is not possible to use for our day-to-day activities. And another thing is that BIPM has provided only 1 kg. And in our day-to-day life, we need various other nominal values, even from milligram to kilogram, even few tons also in industrial application. So everywhere it is not possible. So only 1 kg will not solve our purpose. So we need other nominal values as well. So that's why what we do. And another thing is this, that the NPK is only, this is a national standard, so we cannot use for our day-to-day activities. So that's why we have transfer standard. We have 4 transfer standard, 2 made of nickel chromium and 2 made of stainless steel. So after that, we have working standards, CSR NPL working standard. These are basically 1 milligram to 500 kg. We have in NPL, we have facility from 1 milligram to 2000 kg to provide the calibration services. And there is a method I will explain in next slide. So we maintain this standard working standard. After that, we provide the traceability to the industries as well as Department of Legal Metrology. So RRSL, this is by law. These are legal metrology rules. Every 3 years, they send their weight box to NPL, and only NPL can provide this traceability. They maintain this reference standard 1 milligram to 5 kg, and we provide the traceability. There are 5 regional reference standard laboratory in our country. Definitely Ahmedabad is one of them, and they provide traceability to the secondary standard laboratory. This is under controller of legal metrology. This is at state level, and they maintain this 1 milligram to 10 kg. After that, there's a district level, there's a working standard lab. They maintain 1 milligram to 20 kg, and this is maintained by the legal inspector. They are due to check the commercial weights every year or every 2 years according to the rules to check the commercial weights. And nowadays, if we know that balances are very commonly used for grocery or any other activities like jewelry shop or so. So these are responsibility of the legal metrology to check or verify the weights or the balances every year if these are meeting the requirements of the standard or not. Otherwise, they have right to take the legal action accordingly. And another responsibility of CSR NPL is according to ISO 17025 to maintain the quality system to the enable accredited laboratories, strategic sectors like ISRO, BRC, DAE, Department of Atomic Energy. So we provide traceability to them. So to maintain the scientific metrology, and this part is the basically legal metrology. So this is the hierarchy of the mass standard. And how to derive this the equation to measure the mass. So suppose if any basically calibration, when we talk about the calibration is nothing but the comparison between standard weight and the test weight, and we need a balance as a comparator. So if this setup is kept in a vacuum, so if there is no air in the chamber, so basically when we apply the weight on the pan, so basically this applies some force, downward force. This is a mass into gravity. So this is common for test weight and the reference weight. So when we calculate the difference between these two, so basically when we calculate do the calibration, so we calculate the difference between test weight and the reference weight. But all the applications, most of the applications are in air, because mass or weight is a parameter. It is used in our day-to-day life everywhere. So it is not to create the vacuum everywhere. So if this setup is vacuum in a condition, so what will happen? So one air buoyancy corrects first. So due to air buoyancy, so we'll get some less value from the actual value. So we have to correct it. So this is equal to the volume multiplied by air multiplied by gravity. So this is test weight and the reference weight. So comparison means this is a test weight minus reference weight. So delta F equal to Ft minus F1. So putting all this value. So finally we get the mass value is Mt equal to Mr plus Vt minus Vr into rho A to delta M. So Mr is basically the mass value of the reference weight, which reference weight or reference standard we are using to calibrate the test weight. Test weight means value is unknown. Reference weight means whose value is previously known. And volume of that test weight and volume of the reference weight. I will show one example also on how to calculate the mass value and the uncertainty. And delta M is the difference between test weight and reference weight. But problem is that, as I mentioned, that it is not possible to measure this create vacuum everywhere. So this is the true mass. True word is basically hypothetical word. True, that's why I have put here in bracket. If only mass word is used, that means this is a true mass. So this mass is basically used for the international prototype kilogram, national prototype kilogram, or establish the other standards. But in case of, but to overcome this problem at the same time, when we purchase something, suppose so we purchase gold, so density of the gold is different. If we compare against brass weight, so density of the brass is different. So we have to apply the air buoyancy correction. Similarly, if we purchase the vegetable, we don't know the density of some vegetable or potato. We are comparing against cast iron. So we know the density of the cast iron, but we don't know the density or volume of the potato. And even potato doesn't have any regular shape. So it is not possible to apply the air buoyancy correction. So metrologists have they have to overcome this complicacy. What they have done, one thing, this air density, this 1.2 kg per cubic meter, this is a reference air density in the world. This is at sea level, basically, because in the world, 2/3 portion is covered by the water. So that's why this air density at sea level is taken as the reference air density. How much deviation from this reference air density is multiplied by here. So if our lab is at the sea level, for example, our lab is at Mumbai, so our air density will be very close to 1.12. So in that case, no need to apply any air buoyancy correction. So we can overcome it. So like that, we can eliminate or at least minimize this air buoyancy correction to get the correct value. So this concept is called conventional mass value, or in terms of mass metrology is concerned, mass means is a mass and conventional mass means weight. So this conventional mass is basically used or commonly used everywhere. So that's why weight word is used everywhere, because this is basically the conventional mass. So basic difference between mass and conventional mass is this. Here air buoyancy correction. Here directly multiplied by air density. Here this is difference from the air deviation from the reference air density. And in case of mass of this true mass of reference weight, here we have to use the conventional mass value of the reference weight. So there are two methods to establish the standard weights. One is the subdivision method, other is the substitution method. Subdivision method is used in a special case. For example, as I mentioned, BIPM has provided only 1 kg to us. So we cannot compare the 1 kg against 500 gram or 1 kg against 200 gram. So for the calibration purpose, always nominal value should be same. So we can compare 1 milligram against 1 milligram, 200 kg against 200 kg, 500 kg against 500 kg, 1 kg against 1 kg. But to establish other nominal values, like in our application, we have 1 milligram to 2000 kg requirement we have in NPL. So that case, what we use the subdivision method to disseminate it. So there is a combination of weight is used to compare against 1 kg. So this is a special method is used and special purpose also, U1 class or so. So today I'm not going through the subdivision method because they need special training also for this subdivision method, and this is a very complex method. Actually, I'm not going detail all these things. Just today I will discuss about the substitution method. This is basically one-to-one comparison. So in case of substitution method, this is a comparison between test and standard weight of same nominal value. So for example, if I receive a 50 kg test weight from the customer, what we will do? We'll select 50 kg standard weight. So directly we will compare. So this mass value of standard weight is known. Just simply we will compare it and we can issue the certificate. And other option is that we can use the combination of standard weight also. Suppose 20 kg plus 20 dot plus 20 dot is only for the identification between two weights. Okay, so combination of 50 kg we can compare against 50 kg, but this is used, this combination of weights is used for the higher capacity only. For the lower capacity, like in case of gram or so, we don't use. In case of 2 kg or so, we use the combination of standard weights. So this is acceptable also. So this is a substitution method. So in case of substitution method, so when we do the calibration, so what are our requirements? We need a standard weight. So basically this is a comparison between standard weight and the test weight. So we need a standard weight whose mass value is known, we have certificate, and test weight is unknown, we have received from the customer. And we need a mass comparator or weighing balance for the comparison purpose. And we need a climate station for monitoring our environmental condition, temperature, relative humidity, and the pressure. And there are other requirements also, like anti-vibration table, air conditioned system, room. So I have not included here because just for the measurement purpose, what are the requirements, just we have mentioned here. Now I'm showing one example. Suppose calibration of 20 gram weight, only for the conventional mass, not the true mass, because it is used everywhere. So for the calibration, first we have to note down the environmental condition, temperature, relative humidity, and the pressure, because we should know the air density during the measurement to apply the air buoyancy correction. And every hour we monitor the environmental condition. Reason is that there is a requirement of the standard. For example, various accuracy classes are there. As per YML or 111, the standard is used for the mass calibration. There are 9 accuracy classes. For example, E1 is the highest accuracy. I will show the accuracy, various accuracy classes. So in case of E1 class, temperature variation should not be more than 0.3 degrees Celsius per hour. Even in case of E2 class, temperature should not variation should not be more than 0.7 degrees Celsius per hour. So that's why every hour we should note down the environmental condition to know if this is beyond our permissible limit or not. If this is beyond the permissible limit, so immediately we should stop the calibration and we have to take the precaution. Suppose there is any problem in environmental condition or anything else, so we have to take precautions. So that's why every hour we note down during the period of the calibration. Then we calculate the mean value of the temperature, mean value of the RH, relative humidity, and mean value of the pressure. And using the approximation formula, this is the approximation formula to calculate the air density. Just putting the pressure, RH, and the temperature, we can calculate the air density. There are another formula also. This is the CIPM formula. So this is the most accurate formula in the world, but this is a very complex formula. No need to apply everywhere. In general, we use this CIPM formula for the establishment of our NPK or our transfer standard against NPK, that time we only use. Otherwise, day-to-day purpose we can use, or calibration purpose, even for the highest accuracy class, we can use this approximation formula. So just putting the data, we can calculate the air density. Now just I'm going to show an example of substitution method. There are various cycles. This is an ABBA cycle. ABBA, A means reference, B means test, then again test, then reference. There are other cycle like ABA cycle, reference, test, reference. There are A, B1, B2, B3, up to B5, then again reference. So there are various weighing cycle. These are called weighing cycle. Just here I am showing here ABBA cycle only. So what we have to do? Suppose this is our weight of reference weight or standard weight made of stainless steel, and this is a test weight made of brass or bronze. Just after go back. So initially our balance reading is 0, 0. Now after putting the weight, we have to wait some time. This is called stabilization time. Then we have to note down the reading. Whatever reading is showing, this balance is showing, so we can note down here. Then again, we have to put the test weight here. Now we have to wait few seconds for the stabilization of the weighing balance, and this is depending on the resolution of the balance. If it is a high resolution balance, we need some more time. If it is a, suppose the very coarser balance, suppose in the milligram range or even gram range, in case of few kgs or so, need less time. For example, here I am showing here 1 microgram balance. In that case, we need to wait 15 to 20 seconds. Even it is depending on the environmental conditions also, if there is no air current drift or so. So after that stabilization, just we have note down the balance of the reading. So again, we have to put test. I am not showing here. So again, we have to repeat the test, then the standard. So we have 4 observations, 2 standard and 2 test. Now we have to calculate the difference between test and the reference. So this is basically B minus A. So these are the equation. Either one we can use. Either we can calculate the sum of B and then average of B and average of A, and we calculate the subtract between B minus A. Or we can calculate B minus B1 minus A1 and B2 minus A2 and divided by 2. So either one we can use to calculate the difference. So this is our delta M. Delta M, this is basically the difference between test weight and the reference weight. So this is basically one observation. ABB cycle means these are not 4 observations, these are 1 observation only. So likewise, we have to take the 10 observation, not everywhere we have to take the 10 observations. This is depending on the accuracy classes. We can take 5 observation or 6 observation. This is depending on the accuracy classes or uncertainty we want to achieve. Here I am showing the 10 observation. So we have taken 10 ABBS cycle independently. We have calculated the delta M. So this is a 16 micron. Just I have shown the last 2 digit only to ease the calculation, to minimize the error, all these things. Otherwise, we can calculate 0.0004 times 0 something. So what happens sometimes if we forget to write 1 0 less, or we put 1 extra 0, all the calculation will go wrong. So that's why in our practice, what we do to ease the calculation, we calculate in microgram. The microgram means this is in gram. Then next after 1 decimal, the 3 decimal place is a milligram, and last 3 this is a microgram. So now this is the average of all the 10 observations. So this is basically delta M bar. So mean of all the observations. Now this is our standard weight. For example, this is a box identification of our weight, from which box we used, and accordingly this is the mass value, certified value, and plus minus associated uncertainty. This is taken from the calibration certificate. This will be used to calculate the mass value of the test weight. And So density of the reference weight, since this was made of stainless steel, so this the density is 7.95 gram per cubic centimeter, or in case of kg per cubic meter, it will be 7950 kg per cubic meter. If you go through the standard YMS standard, you will find it, this is in kg per cubic meter. So in that case, it will be 7950 kg per cubic meter, and plus minus this much uncertainty 0.140. So we have to calculate the air buoyancy correction. This is the formula to calculate the air buoyancy correction. This is the difference between volume of test weight and the reference weight multiplied by air density in lab, and how much deviation from the reference air density. This is a rho zero. So first we have to calculate the volume of reference weight. Volume, actually this will be basically VR. So this volume is basically mass divided by density of the reference weight. So here we can take the actual value, certified value of the reference weight, or we can consider the nominal value only. Here we have considered nominal value only, so hardly matters. It will not affect in our measurement. So that's why I have taken here nominal value only, 20 gram divided by this much 7.95. Actually, here I have converted in gram per cubic centimeter because this unit of mass is in gram. So it should be in same unit to avoid the error in the calculation or so. So this much volume of our reference weight. Similarly, we can calculate the volume of the test weight. This is basically mass divided by density of the test weight. So this will be 20 gram divided by 8.4. So this is our volume of the test weight. Just putting this data, we can calculate the air buoyancy correction. So this is 0.006 milligram. So this one rho zero is 1.2 kg per cubic meter. Now the conventional mass value of test weight is MT equal to MR. Already we have discussed MR plus air buoyancy correction is this much formula plus delta M bar. So this is our certified value. MR is the mass of the reference weight. It is taken from the calibration certificate of the reference weight. This is 19.4 times 985. Then air buoyancy correction. We have this is a milligram. Now here converted to gram because our mass value in gram, and this is a 15 microgram. Actually, this is taken from earlier slide. This is mean value. This is the deviation from of the test weight and the reference weight. So this is our mass value of the test weight. So this value is reported in the certificate. So one part is over. This is measured value. So already we have calculated the mass value of the test weight. So this is now known. Now we have to calculate the uncertainty. How much uncertainty is there in our measurement? So first component is the standard answer due to weighing process. This is a type A uncertainty. Actually, there are two types of answer, type A or type B. Type A, basically, these are coming from the statistical analysis. So this is a weighing process. Weighing process, this is the standard formula to calculate the standard deviation. Standard deviation is basically, this is deviation from the mean. So for first one, 16 minus 15.3. So our deviation is 0.7. So we have to square it. So 0.49. Similarly, next one is 0.49. Here 15 minus 15.3. So minus 0.3. If we square it, 0.09. Like that. Individually, we have to calculate the deviation from the mean and the square of each deviation. So this is the formula, this summation of all this value divided by degree of freedom. N is our number of observations. So we have 10. So from this formula, we can get the standard deviation 1.42 microgram. Now standard answer due to weighing process, this is standard deviation divided by root n. So this is a standard formula. This is applicable for all the measurements. This is a common for all the parameters, all the measurement. So standard deviation, this is 1.42 divided by root 10. So this is our one component of uncertainty. This is due to weighing process. So 0.45. In case of mass metrology is concerned, mass measurement is concerned, there are only one type of uncertainty. This is this one, weighing process. All other components are under type B uncertainty. Next one is the standard uncertainty of the reference weight, which reference weight was used to calibrate the test weight. Definitely in case of reference weight, there is an uncertainty because when reference weight was established, that time another reference weight was used, there was some uncertainty. So it is taken from the certificate. Like this is 3 microgram. So expanded, this is the expanded uncertainty at coverage factor k equal to 2. So when we calculate the uncertainty, all the uncertainty should be converted into standard uncertainty. Because sometimes what happens, some laboratory report the uncertainty at various other coverage factors. Usually it is k equal to 2, but not necessarily always it will be 2. It may be 1.96, maybe 2.03, maybe some other value, depending on the effective degree of freedom. I will come after some slide how this effective degree of freedom is affect the coverage factor. So this expanded uncertainty divided by coverage factor. So this is our uncertainty, standard uncertainty due to reference weight. Now next one is the standard uncertainty due to drift in mass value between calibration. Drift or instability. Instability means suppose our mass with reference weight is calibrated in 2022 and it was calibrated in 2 years ago. How much difference is there between two mass values? This is called the drift or instability. For example, drift is 2 microgram. Suppose now this value is 19.4 times 9, 85. Last 2 digit is 85. Earlier its value was 83. That means 2 microgram drift is there. So drift divided by rectangular distribution. So this is our uncertainty, standard uncertainty due to drift in mass value of reference weight. So this is coming from the reference weight. Then standard uncertainty of the air buoyancy correction. This is a very complex formula to calculate the uncertainty. Most complex component actually in mass measurement is constant. So first we have to, as I said, to calculate the air buoyancy correction, we should know the air density. And to calculate the air density, worldwide, even till date, there is no mechanism to measure the air density directly. It is calculated from the monitoring of environmental condition, temperature, relative humidity, and the pressure. Already we have gone through using the mathematical model, we calculate the air density. So that's why we have to get calibrated our thermometer, our hygrometer, and the barometer from the respective department or respective laboratory. So suppose in case of a thermometer, expanded uncertainty is 0.3 degrees Celsius. And definitely there will be coverage factor to change or converted into standard uncertainty. So this is basically expanded uncertainty divided by coverage factor. Similarly for RH and the pressure. And this is the standard uncertainty of air density. And this is the formula according to standard. UF is the uncertainty in formula itself. And this is the value is given in the standard 2 into 10 to the minus 4 into rho A. This much uncertainty is applicable in case of approximation formula is concerned. If we use the CIPM formula, in that case, it is 1 into 10 to the minus 4. Since we have used the approximation formula, that's why it is taken 2 into 10 to the minus 4 into rho A. And after that, this is UP. UP is the standard uncertainty pressure. UT is the uncertainty in temperature, and URH is the in relative humidity, and P is the pressure. This is the mean value. Already we have monitored during the measurement. So this is the mean value, and temperature. This is also mean value in temperature during the measurement. So putting all this data, we can calculate the uncertainty in air density. Initially, we calculated. We have calculated the air density using the approximation formula. Now here we have calculated the uncertainty in air density. And this is the standard uncertainty density of reference weight. Already this uncertainty was associated with reference weight. So 7.95, and this is the uncertainty in density itself. So this value is taken 0.14 divided by coverage factor. So this is the standard uncertainty. So everywhere, first we have to convert it our uncertainty into standard uncertainty. All the expanded uncertainty should convert into standard uncertainty or at k equal to 1. And then standard uncertainty volume, because this formula is in terms of volume. So in case of volume, actually this is basically the ratio of uncertainty in density divided by density, and uncertainty volume divided by volume ratio is same. So from this ratio, we have calculated the uncertainty volume. So basically uncertainty density of reference weight difference divided by density of reference multiplied by volume of reference. So this is already we have calculated from this one. This is our standard uncertainty. This is our density of reference weight of the stainless steel, and this is the volume. Already we have calculated to calculate the volume of the reference weight. So this is the uncertainty in volume of reference weight. So similarly, we can calculate the standard uncertainty volume of test weight also using the same equation. I'm not repeated here. Now we have to put all the value in this formula to calculate the standard uncertainty due to air buoyancy correction. So VT already we have calculated, Dy, uncertainty in air density, then uncertainty in volume of test weight, uncertainty in volume of reference weight, air density in the laboratory using the approximation formula. This is rho 0 is 1.2 kg per cubic meter. So everything's are known. So just putting the value, we can calculate the uncertainty due to air buoyancy correction. So this is our value. So this is the most complicated formula to calculate the uncertainty component. So to eliminate this part, what we can do, we can use the same material in the comparison. For example, if we use the stainless steel test weight made of stainless steel, we can select the standard weight of stainless steel. So we can eliminate it. Or if we have, receive brass weight, brass test weight, in that case, we can select the brass weight or bronze weight if these are available in the laboratory. So we can eliminate it or minimize it, the air buoyancy correction. Otherwise, we have to follow this equation to calculate the air buoyancy correction. The standard answer due to display resolution of the balance. So this is basically the rounding error of the balance. Because when we put the weight on the weighing pan, this is the limitation of the weighing balance. This basically this body has value up to infinity. This is the limitation of the weighing instrument. Thus it is the rounding their value up to 4 decimal place or 6 decimal place or 5 decimal place according to resolution of the balance. This means not that this value is up to 6 decimal place only or 2 decimal place only. This is the limitation of the weighing instrument. So this is basically the rounding error. If last digit is 5, we don't know if instrument is reading it is 0 or 1. So this is called rounding error. So that's why this is resolution divided by 2, half of the resolution divided by rectangular distribution. Multiplied by root 2, this is due to 2 weights because we are comparing 2 weights. One is the standard, other is the test. So this rounding error will affect both the cases, in case of reference weight and in case of test weight. So that's why this is multiplied by root 2. So this is after simplifying it, this is d divided by root 6. So sometimes actually people used to say this is a rectangular distribution because this is the root 6. This is not triangular distribution. This is a rectangular distribution only. Only due to simplification of this equation, it has come root 6. Otherwise, it is a rectangular distribution only. Then resolution, since we used here 1 microgram balance up to 6 decimal place. So 1 microgram divided by root 6. So this is our standard answer due to display resolution of the balance. Now we have to combine all the standard uncertainty we have calculated independently. So UW is the weighing process of type A uncertainty. Dy is the display resolution, drift in the reference weight, UR due to reference weight, UB is the air buoyancy correction, and UD is the display resolution of the balance. So putting all the data, we can calculate the combined standard uncertainty. This is called combined standard uncertainty. Now we have to calculate the effective degree of freedom. Basically, this effective degree of freedom is used to select the coverage factor. So this is a formula, standard formula to calculate the effective degree of freedom. So this is the degree of freedom n-1 multiplied by UC. This is a combined standard uncertainty to the power 4 divided by type A uncertainty. Because all the type B uncertainty, usually this degree of freedom is infinity. So basically this component divided by infinity, it will be 0. So this is, I have shown here simplified equation only. So this value, this is equivalent to infinity. According to YML R111, so if it is more than 20, it is considered as infinity. Here, this is the reason to calculate the effective degree of freedom. If it was 6, then we have to consider 2.52 as a coverage factor. If it is a 20, then we have to consider as 2.13 as a coverage factor. Since it is more than 20, so this is infinity, equivalent to infinity. So our coverage factor is 2. So this is our expanded uncertainty, combined standard uncertainty multiplied by coverage factor. So this is our 4.78 microgram. This is 5 microgram because our instrument up to 6 decimal place. This is 1 microgram. So this is according to GUM. This is an international ISO document regarding the uncertainty, general guidelines for the uncertainty evaluation. So this should be according to the, this should be significant. Measurement result should be significant. Significant means we cannot report more than resolution of the any instrument. So here we have used the weighing instrument with resolution of 1 microgram. So we cannot report up to 7 decimal place or 8 decimal place. We can report up to 6 decimal place only. We can reduce the place. We can reduce this mass value up to 4 decimal place or 5 decimal place, but not beyond the 6 decimal place. This is the uncertainty budget. This is basically tabular in tabular form. This is the requirement of the standard. We can show all the component of the uncertainty, all the factors, even source of uncertainty, estimated value, if there is any limit, and then distribution, divisor, the sensitivity coefficient, all these things. Already we have calculated so many complex formula using a complex formula to calculate the uncertainty in previous 5-6 slides. So here in one slide, we have shown all the things. So from this table, we can see the all the gist of the uncertainty calculation. So this is our final value, conventional mass value of 20 gram weight. This is our measured value plus minus. This is the uncertainty. So first we have to decide the decimal place of the uncertainty, and accordingly we have to rounded off the measured value. So here our uncertainty is up to 6 decimal place according to our equipment, weighing instrument we have used, and accordingly we have this rounded off our measured value as well. So this is our reported mass value, what value we report in the certificate. If we have to do the classification according to YML R111 standard. This is the maximum permissible error of the weight according to YML R111. YML means International Organization of Legal Metrology. So this is a free document. Anyone can download it. Just putting in Google YML R111, you can find it. It's a free document, and there are 9 accuracy classes: E1, E2, F1, F2, M1, M12, M2, M23, and M3. And 9 accuracy classes. E1 is the highest accuracy class. These are classified according to the application. Like E1, E2 class, in general, it is used in pharmaceutical industries. Then F1, F2 in manufacturing industries. Then commercial purpose, we use the M accuracy classes. E means extra fine, F means fine, and M means moderate. So these accuracy classes are divided according to the application of the weights. So there are two requirements as per standard to classify the weight. One, expanded uncertainty should be 1/3 of the MPE, maximum permissible error, and conventional mass. This should be nominal value minus delta M is the MPE, maximum permissible error, minus expanded uncertainty. So this is called error. So there are two requirements. If our measured value and the uncertainty is meeting both the requirements, then we can say, yes, this weight is meeting the requirements of the standard. And that case, we can provide the compliance in the certificate. If not meeting the requirements, in that case, we mention that this is not meeting the requirements of the standard. So just I would like to explain a little bit more. For example, in case of 1 kg, so for E2 class weight, our MPE or delta M is 1.6. 1.6 milligram is the limit, plus and the minus. Now uncertainty should be less than equal to 1/3. 1/3 means this is almost 0.5. So if we go through this table, we can find these are already almost ready table for the 1/3. Either it is exactly 1/3 or close to 1/3. So here we consider 0.5. So what we have to do? We have to subtract delta M minus expanded uncertainty, like this one, delta M minus. So our mass value should lie within this 1.12. So basically, reason is that 1.12 is our error limit. Error plus expanded uncertainty should be within the MPE. Should not be more than 1.6. So that means if our measured value is in this zone, within plus or minus 1.12, then it is okay. If it is beyond this, for example, it is 1.17, that means this is more than 1.6. So this is out of the permissible limit. Now question is here, if it is within the 1.6, then what to do? As per standard, this is called conditional pass or conditional fail. But according to this YML standard, if we apply the uncertainty, since this is after applying this uncertainty, this is beyond the permissible limit, is 1.6. So here we consider as fail. So in the certificate, what we do, we mention this weight is not meeting the requirements of the YML 111 standard in this accuracy class, like that. So there is no ambiguity because standard has given a clear-cut guidelines how to give the compliance. Otherwise, there is another option. Since standard says this is less than or equal to, this is not mandatory, only equal to. We can reduce the uncertainty also. Even in case of 0.5, we can reduce to 0.4 or 0.3. But we have to analyze the risks also. According to ISO IC 17025, 2017 version, those who are already familiar with this standard, you know, now this is basically risk-based thinking. Now here we have to analyze the risk. How much risk is there? Reason is that not only measured value here or this uncertainty we are providing to the customer. At the same time, we are providing the validity of the certificate. 2 years, 3 years. Suppose if we are giving the validity of 2 years, we don't know if we reduce the uncertainty, it will be valid for 2 years or not. So here need to analyze the risk. So this is up to the laboratory. In our NPL practice, if it is inherent in the standard, then only we can provide the compliance. Otherwise, we don't provide. In case of weight is concerned, since it is clear-cut guidelines, this is inherent in the standard YML 111. In that case, we provide the compliance. In some other parameter, we don't provide any compliance. So this is all about the weight. Now in continuation, just calibration of the balance. After that, you have any clarification or any question, we'll go. So this is a calibration of balance. Basically, for the calibration of balance, we need standard weight. So this is a vice versa. For the establishment of the reference weight or standard weight, we need suitable balance. And for the calibration of balance, we need suitable weight. So for the balance, these are the requirements, very basic requirements. An area which is free from the vibration and excessive air currents, where changes in temperature and relative humidity are minimal, is selected. So balance should not be placed just under the split AC or just before the window AC. You will find that balance is not stable. So we'll place the balance away from the air conditioned system, but air current effect is minimal. Balance should be placed on a sturdy stone table. We should have a stone table, marble table, or granite table, or anti-vibration table we can use, or we can make the concrete foundation also in case of high resolution balances or comparators. The floor should be rigid and preferably be the ground floor to resist the vibration effect, or we can select the basement also, ground floor or the basement, to resist the vibration effect and the measurement. High resolution balances must also be relabeled using the level indicator each time they are moved to different location. There is a spirit level always, it is attached with the balance. So always we have to check when it is shifted from one location to other location, but it is not the good practice to shift the balance after calibration. So that's why I have mentioned here, balance should be calibrated at site only, where it is actually used. After calibration, if you relocate the balance, that means this calibration certificate will be invalid. Suppose if balance was calibrated the ground floor, if it's shifted in second floor or third floor, so balance calibration will be invalid. And that's why mobile facility is not allowed in case of balance calibration is concerned. So that's why what we do, always we provide calibration services at customer premises only. We carry our standard weights and using our standard weights, we provide the calibration. Because there are G factors and air density, there are various other factors. So balance should be calibrated at that location where it is actually used. So customer or user first decide at which location balance should be used, and after that they should get calibrated it from the NPL or any other laboratories. Classification of weighing instrument. Usually we use various terminology in case of weighing balances or weighing instruments are concerned. Precision balance, ultra micro balance, micro balance, semi micro balance. So various terminology we used in case of balances are concerned. But according to YML R76, in case of weight, there is R111. In case of balance, this is R76. So there are 4 accuracy classes: special, high, medium, and ordinary. These are the symbol class 1, 2, 3, and 4. This is not Roman 4. This is like 4 times 1. So these are symbol used on the instrument, and these are the symbol used on the standard. This classification are basically on the basis of the verification scale interval. This verification scale interval is E. This is in unit of mass, either gram, milligram, microgram. These are in same unit. And this deviation is basically used for the classification and to calculate the permissible tolerance or maximum permissible error. Only 2 reasons: only to classify the instrument and to calculate the maximum permissible error of the instrument. So usually E value is provided by the manufacturer, and this is a requirement of the Department of Legal Metrology in our country. This is a mandatory requirement. Manufacturer has to provide the E value on the label or tag of the weighing instrument. In case of laboratory balances, in case of this scientific metrology concern, if we use them micro balance, like 1 microgram balance, 10 microgram balance, usually it is not given. These are basically the class 1 instrument. In case of class 1 instrument is concerned, this class 1 instrument means if resolution is less than equal to 1 milligram, and every time and for always E value will be 1 milligram. So any weighing instrument, if resolution is less than equal to 1 milligram, E value is 1 milligram. Reason is that even till today, according to YMLR 111, lowest nominal value is 1 milligram, because it is not possible to go below the 1 milligram till date. Physical weight, because sometimes even 1 milligram, 2 milligram, when we do the calibration, it is a fly away. It is so small, sometimes it is not visible even. So that's why YML has restricted it up to 1 milligram only. So in case of class 1 instrument is concerned, it is always 1 milligram. In other classes, mostly it is provided by the manufacturer. If it is not provided, in that case, we can consider as E equal to D. Whatever our resolution, we can consider as our E value. Now this is the MP to calculate the maximum permissible error. For example, in case of class 1, we know E value is 1 milligram. Just simply we have to multiply this constant value multiplied by E value. So 50,000 milligram. So up to 50 gram, our MP is 0.5 milligram. 50 gram to 200 gram, our MP is 1 milligram. More than 200 gram, our MP is 1.5 milligram. So similarly, if we know the E value for other accuracy classes, then we can calculate the MP for all the accuracy classes for that particular load. So this is the only application of the E value. First, the classification of the weighing instrument, and to calculate the MP. Because if we don't know the MP, then we cannot say our balance is meeting our requirements or not. So we should know the maximum permissible error at that particular load. And another reason is that to select the standard weight, which standard weights are suitable for the balance calibration. So to select the standard weight, first we should know the MP of the weighing instrument at that particular load. So first criteria of the standard weight is it should meet the requirements of the YMLR 111. It should meet the requirements of the YMLR 111, means E1 class, E2 class, F1, F2, whatever accuracy class are there, it should meet the requirements of the R111. Then they shall not have an error greater than 1/3 of MP of the instrument for the applied load. For that particular load, this error should not be more than 1/3 of the MP. If they belong to E2 or better means E1 class, their uncertainty rather than their error is allowed to be not greater than 1/3 of MP. So there are two conditions. In case of E1 or E2 is concerned, uncertainty should be less than equal to 1/3. If it is F1 or lower accuracy class, in that case, error should be 1/3 of the MP. So just I am showing one example how to select. For example, class 1 instrument, in case of 50 gram load is concerned, already we have calculated MP is 0.5. Already we have calculated here from this table 50 gram, our MP is 0.5 milligram. So for both the cases, this is 1/3 of MP. So 1/3 of MP is 0.16 milligram. So for E1 and E2 class, standard uncertainty of the standard weight should not be more than plus minus 0.16. So there is no confusion, anything. It's very simple. Only thing is that in case of F1 or lower accuracy class, so standard error of the standard weight should not be less than equal to 0.16 milligram. So basically plus or minus here also mass value. So mass value should be within this in case of F1 class is concerned. So basically this is our MP at that load. Then 0.16 or so in case of F1 or lower, F2, M1, M2, whatever weight we are using, standard weight we are using for the balance calibration at that particular load. So our mass value should lie in this green zone. So as per YMLR 111 standard, if it is between this blue line and the red, this dotted line, is also meeting the requirements of the F1 class. But we cannot use as a standard for the calibration of balance of class 1 instrument. So this is the reason. So although in between 0.16 and 2, this is meeting the requirements of the F1 class or F2 class. There is no problem at all according to standard. But these standard weights are not suitable for the calibration of the class 1 instrument at that particular 50 gram load. So that's so our mass value should be within this zone, green zone. Then only we can use it. So this is basically in sequence. First, we should know the E value. Then using the E value, we have to calculate the MP. Once MP is known, then we can calculate the error at, or uncertainty at that particular load, like that. Now here I am showing one example of test procedure of non-automatic weighing instrument. For example, maximum capacity is 1 kg, minimum capacity is 0.2 gram. Just I have selected this specification to show all the experiments. Readability is 0.01 gram or 10 milligram, assuming that E value was not given. So assuming here this is equal to D, then repeatability, for example, it was given, then linearity, then drift in balance, how much reading will change for every change of temperature per degree Celsius. There are various test methods as per YMLR 76, but those are directly affecting our mass measurement. I have highlighted here only. There's a 3 tests I have selected. There's a weighing performance test or linearity test is the first one, then eccentricity test and repeatability test. So this is weighing performance test. Actually, according to YMLR 76, they don't use the terminology linearity. So that's why I've written here weighing performance test. Otherwise, it is linearity test also. So we have to apply the test load from 0 up to the maximum. And similarly, we have to remove the weight back to 0. So this will be basically gradually increasing and gradually decreasing. And we have to select the weight. At least 10 load we have to select, and we can discuss with the customer according to their application before selection of the weights. So for example, I have shown here 1 kg balance. Suppose customer has this balance of 1 kg capacity, but they are using up to 500 gram only. So we can calibrate it up to 500 gram also. So after discussion with the customer, we can select the load accordingly. So here there are conditions. We have to select the maximum capacity, minimum capacity, and value at or near those at which MP changes. So, and every time we have to note down the environmental condition also, temperature, RH, and the pressure. Now this is the 200 milligram. This is the minimum capacity of the balance. Then this is the maximum capacity of the balance 1 kg. Then we have selected the load 550 gram, because at 50 gram load has this MP has changes from 0.5E to 1E, and then 200 gram here 1E to 1.5E. So after that we have selected this load to cover all the range. In some cases, some standard says we can select the 10%, 20%, 30% like that. But problem is that in case of 1 kg, 10% is 100 gram, there is no problem. In case of 20%, this is a 200 gram. But in case of 30%, this is a 300 gram. And at the same time, standard says it is preferably to use the single weight. In case of 300 gram, we cannot use the single weight because we don't have any single weight. We have to use combination of weights. In case of 400 gram, we have to use the combination of weights. So like that. So that's why. And suppose customer is using this balance even lower than the 100 gram. We are not able to know the linearity error at that particular load. So that's why to cover whole range, we have used the load from minimum capacity to the maximum capacity. Now, what to do? For example, if the most of the cases you will find the initial value is 0. But assuming that suppose there is some mechanical error, we are not able to make it 0. Some error is there. So we have to note down this value. Is a error at 0. Reason is that this value will affect in our subsequent measurement. So every time we have to apply the correction. So that's why we have to note down this error. Now we have to place the weight 200 milligram on the pan. Then after stabilization, we have to note down the balance observation 0.20. Now we have to apply the additional load, or this is called sensitivity weight. So sensitivity weight or additional load, this is basically 1/10 of the resolution. Our resolution of the weighing instrument is 10 milligram. So that means 1/10 means 1 milligram. So that's why I have selected here 10 milligram. If resolution of the balance was 5 milligram, the 1/10 means 0.5 milligram or 500 microgram. Physically, 500 microgram weight is not available as per standard. So that's why I have selected here 10 milligram. In that case, we can eliminate this additional part. If this is the balance resolution is lower than 10 milligram, so no need to apply this additional load. So how to apply? First, we have to put the 1 milligram. Suppose there is no change in our observation, then we have to replace 2 milligram, no change, 2 plus 1, 3, 2 plus 2, 4, no change. Now just after putting 5 milligram, next reading has come. So it is understood that next reading will be 0.21. So no need to note down this reading, but we have to note down after applying how much load next reading has come. So that's why additional load is 0.005 gram or 5 milligram. So that much load we have to mention here. Now we have to remove the additional load, but main load still on the weighing pan. Here standard says this will be gradually increasing or progressively increasing. So that means first we have to place the next load, that is 500 milligram. Then we have to remove 200 milligram. So here we need very practice or skill to develop with time, because that time you will find you are not able to place the weight exactly at the center or so. So we need practice to develop the skill. So first we have to place the 500 milligram. Then we have to remove the 200 milligram. And similar way, we have to apply the additional load. I am not showing here. Then 1 milligram, 2 milligram, 3 milligram. In same fashion, we have to apply the additional load. So like that, we have to go up to maximum capacity and return to 0. So basically, our measurement will start from the 200 milligram and will finish at 200 milligram. So this arrow is showing the actual direction from 200 milligram, 500 milligram, like that. And this is the upward direction. Now we have to calculate the error in each and every load. So this is the formula I plus half E minus delta L minus L. So I is the indication. Then half E is if 10 milligram, 0.01 gram is our E value. Then this will be 0.005 minus delta L, this is the value, and minus load. So we can use the certified value of the standard weight. So we can calculate the error. So this is our error at that particular load. Since in our initial measurement or at no load condition, our error was plus 0.01 gram. That means in our all the measurement, this value has been added. So we have to subtract it from the error. So this is the corrected error. If it was minus, we have to sum, or if it is plus, we have to subtract. So just error, we have to correct with the opposite sign. So it's all the error, corrected error should be within the maximum permissible error, which already we have calculated using that table, MPE table. If not, in that case, we can mention is fail. According to legal metrology, we mention pass or fail. But in case of scientific metrology is concerned, when we issue the certificate from the NPL, we don't provide the pass or fail. What we do, just simply we mention the value, this much uncertainty, this much error against the MP of this much. Let customer decide what to do with this weighing instrument. If they want to get repaired it due to some reason, further they have to calibrate it, or suppose they were purchased this balance for calibration of E2 class. If these are not meeting the requirements of the E2 class, they can use for the F1 class. This is up to the customer what they want to do. So we don't mention this is a pass or fail. Just simply what we do, we mention that this is the error against the MP of this at that particular load. Next one is the eccentricity test or obcentric test. So basically, we place the weight at the various location on the weighing pan and calculate the error, because our aim is to place the weight at the center. But sometimes what happens, balance is used everywhere in industrial application, in our day-to-day life. All the products or all the components are not in the same shape, regular shape. This is a spherical shape or rectangular shape or various shape, different shapes. So center of gravity may be different object to object. So that's why we should know the eccentricity of error of the balance. So this is the eccentricity test. This will be basically 1/3 of the sum of the maximum capacity and the additive tear effect. So basically what happened, most of the cases manufacturer does not provide the additive tear effect. So that's why what we do, we consider 1/3 of the maximum capacity of the balance. Not exactly 1/3, is close to 1/3. And here largest weight should be used in preference to several small weights. For example, in this case, our balance capacity is 1 kg. This is 1/3 means 333 gram. So in that case, we have to use 200 gram plus 100 gram plus 20 gram plus 10 gram plus 2 gram plus 1 gram. So unnecessary stacking should be avoided. What will happen? Suppose if one weight is fall down, weight will damage. At the same time, your balance also will damage. So in that case, we can do one thing. We close to 333 means 300 gram we can use. Select. Because standard also says smaller weight shall be placed on the top of the larger one. So you have to place smaller weight on the top of the larger one. But you have to be very careful, because due to friction between two weights, in long run, your mass value will change. So here also we need practice, how to apply the load. You need to develop the skill. So here also, assuming that there was some error at 0. Now balance is divided into 4 segments. So this a visual inspection is sufficient, or suppose you can mark is also use sketch pen or any marker or anything. You can mark it also, or visual inspection is sufficient. So what to do? Now we have to place the weight. Here I have selected here 300 gram, not 333 gram, only 300 gram. As standard says, unnecessary stacking should be avoided. So 100 gram is placed on the top of the 200 gram. So this is our value. We have noted down 300.02. Now similar way, we have to place the additional load. 1 milligram, suppose no change. 2 milligram, no change. Just after putting 3 milligram. Now next reading has come. That means we have to note down 0.003 gram. So now we have to replace all here, remove all the weights. Now we have to place the weight in segment 2. So basically here 1 means center, then 2, 3, 4, 5, then center, then 5, 4, 3, 2, 1. So this is basically clockwise and anti-clockwise. Now we have to place the additional load. Just I am showing it directly 5 milligram, but we have to use 1 milligram, 2 milligram, like same fashion we have to use. But here just example to save the time, I am showing directly the 5 milligram. So we have to note down the 5 milligram. So likewise, we have to apply the load in various segments, and every time we have to apply the additional load, and here we have to note down our observation. And then again we have to calculate the error using the same formula. Then we have to correct it, apply the this error at zero load. Now this is the corrected error. Now we have 3 observations at position 1. At initial, then in between, and final. Then we have 2 observations each for position 2, 3, 4, and 5. Now here we have calculated the mean value. For position 1, there's a mean of this 3. Then position 2, mean of 2 observation, because there's a clockwise and anti-clockwise. Then we have to subtract the value. We have to calculate the error from the center, because our aim is to place the weight at the center, not here and there. So how much deviation from the center? So we have to calculate segment 2 to segment 1, segment 3 to segment 1, segment 4 or location 4 to location 1, and location 5 to. So we have 4 segment or location and 4 deviation. So which one is maximum? This is our eccentricity error. So this one is maximum. If it was minus, even in case of minus also, yeah, this is modulus of this value, plus or minus, we have to consider the numerical value. So this is our maximum deviation. So this is the eccentricity error. This value is reported in the certificate with against the maximum permissible error at that particular load. Then the repeatability test. Repeatability test is normally carried out in 2 loads, 50% load or half load and the full load. So half load, or this is the 1 kg balance, so half load is 500 gram. So one weight we can repeat 10 times. So just simply we have to repeat the same weight. Yes, this is our observation, and I have not shown here additional load. This is the same fashion we have to apply the additional load, then repeat it, and again we have to place. So we have to repeat 10 times. Then we have to calculate not error. This is a P. P value is basically the corrected observation after applying additional load. Then here the maximum minus minimum value. This should be within the MP as per that table. If not meeting the requirements, beyond the MP, then we mention here fail. But definitely in this is for the legal metrology purpose. But in case of scientific metrology, we, as I mentioned, we don't mention pass or fail. Just simply we mention this much value, observed value is this much against the MP of this much. Now similarly in full load for 1 kg, we have to repeat the 1 kg load 10 times. Then we have to calculate the maximum minus minimum value, and this value should be within the MP. Now we have to calculate the uncertainty. Already 15 minute balance complete. So this is the example of uncertainty calculation. Just I have shown here only for 1 kg, but we have to calculate the uncertainty at different loads. At least for the 10 loads, we have used for the weighing performance or linearity test. So this is a few components are common as weight calibration. First one is the standard answer due to weighing process. It's the same formula to use for the to calculate the standard deviation. So this is the value. So this is corresponding to 1 kg. So this is calculated from 1 kg. In case of 500 gram, we have to consider the standard deviation from the 500 gram. And in case of other nominal value, for example, 200 gram, 100 gram, we can calculate, consider the standard deviation of the 500 gram. And as standard says, I forgot to mention, as standard says, this test should be carried out at half load and the full load. But at the same time, we can consult with the customer if they need to get calibrated or this repeatability test for any other nominal value, like 100 gram, 20 gram, 200 gram, like that, according to their application. So we can do that also. Not necessary only we will calibrate, do the repeatability test at half load and the full load. We can do the other nominal values also. This is applicable. So similarly, when the standard deviation is known, the standard deviation divided by root n is the our type A uncertainty or due to weighing process. So same as weight, then standard answer due to reference weight, which reference weight was used to calibrate the balance. So this is corresponding to 1 kg. So independently, we have to calculate the uncertainty at each and every load. So now we are talking about the 1 kg. So this is corresponding 1 kg expanded uncertainty. 1 kg is considered. So expanded uncertainty divided by average factor. Similarly, standard answer due to drift in mass value between calibration, as I mentioned. If our standard weight was calibrated 2 years ago, and again it has calibrated this year, how much deviation is there, difference is there in mass value. So that is called drift, or also called instability. Theoretically, it should be same, but in practical, it is not same. So how much deviation is there? So drift divided by rectangular distribution, this is our uncertainty component. Standard answer due to drift. Then answer due to display resolution. Here deviation is from the weight d divided by 2 root 3 only, not multiplied by root 2. Reason is that in case of weight calibration, we use 2 weights. One is the standard weight, other one was test weight. But here, in case of repeatability test, only 1 weight was repeated 10 times. So that's why this is d divided by 2 root 3. That means rounding error is affected 1 time only. So sometimes laboratories make mistake. In this case also they multiplied by root 2. If we use the 2 weights, here also we can use the 2 weights for the comparison. In that case it will be root 2. So this is case to case basis. Standard answer due to drift in sensitivity due to temperature. Sometimes this is not provided by the manufacturer. If this is not provided by the manufacturer, we can eliminate this part because we are not able to calculate the uncertainty component. If it is given, for example, it is given 2 ppm per degree Celsius. That means in 1 degree Celsius change, our mass value is changed by 2 ppm. So this is in case of 1 kg. So 2 ppm means 2 into 10 to the minus 6 multiplied by nominal value. And this is the temperature variation. Already I have shown in the table. We have to monitor the temperature, RH, and the pressure during the measurement. So how much deviation was there during the measurement in the temperature? Suppose our measurement was carried out for 1.5 hours. So how much deviation was there in temperature? So this multiplied by sensitivity coefficient multiplied by nominal value. In case of 500 gram, it will be 500 gram. In case of 100 gram, it will be 100 gram. So divided by root 3. So this is our component. Standard answer due to eccentricity loading or eccentricity error. So this is eccentricity error. Which one is the maximum? 0.022. Already we have calculated, taken from the eccentricity error, and this is the standard formula. This is already available in YML at 111. D1 by D2 multiplied by capital D divided 2 root 3. So D1 is basically from center of the balance pan to the center of in this segment. For example, this is segment 2 or position 2. So in this segment, so sometimes what happened, suppose human error is always there. So if we are not able to place the weight at the center or close to center, but sometimes what happens is not possible to measure it. Only few error is there. So no need to worry. We can consider it as half. So this is basically this center to center of this segment and center to this basically radius. Or in case of a rectangular shape also, this is center in this segment. For example, if this is our weighing pan, so from this to this is our center point and center to corner. So it will be half basically D1 by D2. This will be half multiplied by this eccentricity error divided 2 root 3. So we can calculate the standard answer due to eccentricity error or eccentric loading. standard answer due to linearity. Actually, few standards says linearity may be avoided or we can no need to consider as an uncertainty component if we are considering as a correction. If we are applying the correction, we can eliminate this part as an uncertainty component. But I have shown here because this is depending on the application. So because in case of some application, they don't apply any linearity correction. So in that case, linearity this factor is taken as an uncertainty component. So linearity factor, this is corresponding to 1 kg. This is taken from the weighing performance test divided by √3. Then this is a combined standard uncertainty. All the factors are combined. This is a sum of square of all the individual component. UA, type A uncertainty or weighing performance. Then UR reference. Dy.Ir is the drift. Then UD is the display resolution. Sense is the sensitivity of the this coefficient, and eccentricity and the linearity. Then putting all the data value individual component we have calculated, we can get this is the combined standard uncertainty. And similarly, we can calculate the effective degree of freedom. Then from the effective degree of, this is common for weight and the balance. And from the effective degree of freedom, just we can select the coverage factor, then combined standard uncertainty. This one multiplied by coverage factor, we can get the this expanded uncertainty. Once again, we have rounded off this value since our resolution of the balance was 0.01 gram up to 2 decimal place. So that's why instead of 0.038, we have rounded up to 0.04. And once again, I would like to mention here that if uncertainty should not be rounded down, always it should be rounded up. If it was 0.32, for example, in that case also it should be considered as 0.04, not 0.03. In normal mathematics, what we do, if it is less than 5, we consider the lower value. If it is more than 5, we consider the higher value. But in case of uncertainty is concerned, this is the guidelines as per ISO GUM. Uncertainty should not be rounded down. In exceptional case means, for example, 0.0302, very close to 0.03. In that case, we consider as 0.03. But if it is 0.031, even 2, so we have to consider as next higher value. So uncertainty should not be rounded down. Always it should be rounded up. And similarly, this is the uncertainty budget to show all the sources of uncertainty, estimated value, all these things are shown in this tabular form. And this is our final value, reported uncertainty at 1 kg load, plus minus 0.04 gram at k equal to 2. So this is for 1 kg only. So similarly, for other nominal values, we have to calculate the uncertainty independently. In case of 500 gram, we have to calculate the uncertainty at 500 gram because reference weight of 500 gram will be different from the 1 kg. In case of 100 gram, standard uncertainty will be different from the 1 kg. So only uncertainty at maximum capacity is not to fulfill the requirements. Sometimes what happened in case of balance, this volume parameter is concerned. Standard says respective standard of the volume, like in case of micropipette ISO 8655 and in case of glassware ISO 4787. Standard says is uncertainty should not be more than 6 times the resolution. So what happened if you calculate the uncertainty at maximum value, you will find always you are not able to meeting the requirements of the 6 times the resolution. So we have to calculate, for example, 1 microgram, 1 microliter. It is equivalent to 1 milligram. So if you are using the capacity of the balance is 100 gram, and if you calculate the uncertainty as 100 gram, definitely you will not be meeting the requirements of 1 milligram, which is corresponding to 1 microliter. So this kind of things happen. So that's why for all the loads, independently, we have to calculate the uncertainty and we have to report independently. So thank you very much for your patience.
Thank you very much, sir, for your kind discussion and explanation of this somewhat complicated topic of calculating measurement uncertainty. Thank you very much, sir. Actually, some of, or I think all of the certificates of the last program has been issued on their mails. If somebody has not received the mail and he has not received the last certificate of the training program, either he has not attended the program in all the batches, or he somewhere there is some error in his mail ID. My request is, if some email me, my mobile number, everything is available on all the pamphlets which we will discuss it on how uncertainty calculation is concerned immediately after this program, or we will be back tomorrow, because I remember I forget the last training programs for these presentations also. I will share it now, and secondly, immediately after this program, we will share the presentation today, and let me know where this presentation to all the participants. At this 2 o'clock, what we will do, we will discuss discuss in now we'll on the, so that everybody can understand how it can be calculated. Now we will assemble at clock. Thank you.
लाइट ऑन कर देना. When we are doing the mass measurement, length measurement, volume measurement, even if you are calibrating the electronic balances, so there is a lot of importance of this measurement of uncertainty. And suppose if you are using the balances and you are calibrating a calibrate, burette or pipette or something like that, and then you are going to measure its accuracy. So there is a temperature factor and the mass value what you are taking, the water and other factors relating to your rooms and the instrument what you are using. So all these parameters you have to take in while you are calculating the measurement of uncertainty. In general, the measurement of uncertainty should be half of the maximum permissible error. But in some cases, in most of the cases, it has been recommended that it should be 1/3 of the maximum permissible error. So it means that when you are maintaining your equipment, so you should clear that what are the performance of your equipment. All the equipment in your laboratory used for testing of this mass measurement, volume measurement, thermometer measurement, or any type of measurement. So lot of instruments are being used. So every instrument's measurement of uncertainty is required. Then after that, you have to calculate the standard deviation, and that will be the final standards of measurement of uncertainty for that very instrument. Suppose if you are doing the electronic balance, so for the electronic balance, you have to calculate the measurement of the uncertainty. For that, you have to take the repetitive values and the eccentricity test and so many other type of test, and then temperature test, and what is the uncertainty of your artifact, and then the combining all those very things, and due to temperature, are there any measurement of uncertainty, or suppose humidity also there may be the issue of the uncertainty. That's the reason the temperature is defined for the laboratory 23 degree plus minus 2 degree. So this is the international practice. So people are keeping those very things. In spite of that, but you have to do the measurement of uncertainty because you are not knowing that the reasons why the uncertainties are coming. Uncertainties are coming. It is true that the use of the instrument, but whatever the instrument are coming, it is neat and clean. It is verified. It is well functioning. Is giving the correct accuracy. All the parameters are there, but in spite of that, we say that measure the measurement of the uncertainty. So this is the very important things, not only to maintain your the equipments or do the calibration work or any other type of things, but also to maintain the very good laboratory practices. The measurement of uncertainty, suppose if you are doing, so for that in your laboratory you can measure the different artifact are having the same mass value, and then you calculate the measurement of uncertainty on that very things. So you may find your approach that suppose in two laboratories the same mass accuracy artifacts are being given, but when you are doing the uncertainty you are finding the different values. So if you are finding the different values, then it is matter that there is something difference in the measurement process. So in that very process, you have to think that from where these values are differing. Even if they are within the tolerance limits, then it's okay. But in spite of that, for the long run, it is not good. So you have to measure the all the equipments and their uncertainties, not only the mass value, mass artifact measurement or the electronic balance artifact. These are the things. So you have to keep in mind that whatever the equipments are being used, everything's measurement of uncertainty should be there in the your laboratory. And when you are doing the calibration work, then that measurement of uncertainty concept may be applied. Apart from that, there is a software for the measurement of uncertainty that also you can have, and while doing the calibrations, you can use that very software, and easily you can find out the measurement of uncertainty. Only you have to find out the value, and that value you have to place in that very calculator, and the things will be done. So by this way, you can do the measurement of uncertainty. I hope that the measurement of uncertainty is a very good topics for the laboratories, and all laboratories should be adopted. And by this way, they can themselves identify the level of their accuracy of their laboratory, and how much they are near to the standard value, and all that things they can know that very things. So this is the important criteria, and now these days everywhere people are doing. So I hope that it has not reached to all the laboratories. So Mr. Ashutosh Agarwal has taken the steps that how this measurement of uncertainties and other standards value, non-automatic and automatic weighing instruments, all these he will take the workshop on many topics as he may think it necessary for the industries uh, who are approaching him, and what is the requirement of the laboratory. So I am very thankful to Mr. Ashutosh Agarwal and to the scientists who are participating in this conference, and all the dignitaries also who are participating in this conference. I am very happy that this is well organized conference, and I wish that it will be very successful, and I give wholehearted thanks to Mr. Ashutosh Agarwal. Thank you. Thank you, Mr. Ashutosh ji. Thank you, Ashutosh ji.
Ashutosh sir.
all the participants to all the
वॉइस नहीं आ रही है आपकी, वॉइस नहीं आ रही है.
Okay. Thank you. Thank you very much, sir, for your kind words. Certainly, we are trying our best to disseminate the information to all the members, to all the laboratories, and the assistant officers who are actually working in the field for the image and balance. Later on, students will move in the temperature, electrical parameters, and all the parameters students will move parameters. How to calculate the measurement uncertainty? As Dr. has discussed the morning, in a very precise and well manner, how to calculate uncertainty in the mass and the balance. I'm giving just an example with the help of this balance. I think your camera is not focused on the indication. Yeah, can you focus it on the indicator? Yes. So we are having this balance available with us. With the help of this balance, we are going to calculate a 20-gram weight. We are having even class weights. With the help of this even class weight, we will calculate issue class weight of 20 grams. First of all, what are the requirements we have to measure? What I'm just writing. Let's say what is my date of the time, temperature, relative humidity, pressure, and air acidity. These are the parameters which we are going to take for before the calibration. Let's say the date today is 3rd of May 2022, and now the time is 2:25 p.m. Let's say what is the temperature? Can you show the temperature? Let's say it is 25.6 degrees Celsius. What is the relative humidity? You just show on the indication. Just show the camera. Yes, what is the humidity?
35%.
Sorry?
35%.
35%.
Yes.
Okay. Pressure? Is the help of your barometer?
Yes, sir. 989.
989 in terms of millibar.
Yes, millibar.
And the air density, we are taking this in terms of OA, milligram per centimeter cube, which we are taking 1.158, but which we have already calculated. How we calculated this density? We have the formula. Rho A is visible. Rho is visible in the in your mobile. Below the 0.0 34848 into pressure P minus 0.009 into RH into exponential of 0.061 into T divided by 273.15 plus T. So this is the formula for the calculation of air density, which we generally calculate whenever there is a change in the density of the material of the test rate and the reference rate. Let's say it is 2.25, and I'm just taking the next example because the observations are already available with me. I'm not taking this observation, I'm just taking the observation available with me. Let's say at 335, the temperature will get in, let's say 25.8, humidity, let's say we are saying 35.1. It is also about 987, and similarly we will calculate the air density. So basically the air density, when we calculate all these values, we can calculate what is the value of this air density. And let's say we are taking after 435, the value is similarly I can take all the values and I can calculate the density of air, rho A. This is a table which is very simple. Time, date, temperature, humidity, pressure, and density. This is all parameters which are available with us with the help of a standard humidity meter. We can measure all these temperature, pressure, and humidity. Nowadays we are having catalogers with catalogers where we are measuring all these quantities. So similarly, this is the way first of all we need this all values available with us so that we can do the calculation. And removing it, I'm using this calculation of Mandasa only because these are the readily available calculations with me. I'm just taking the same example. I don't have to do any calculation. The Mandasa also discussed the morning let's share this presentation today, and you will find that the calculations also are made. This is a Mandasa presentation. Now, as we are using this substitution method, we are doing therefore because for our even survey we used to perform this substitution method. Otherwise, for any other stage, we used to do substitution method. Substitution method is very simple: AB, BA, or ABA. So generally, we used to perform ABBA method. Let's say A is our reference, A1, B1, we call it test, then B2, again test 2 and A2, that is the reference value of 2. If you place the value of the 20 gram on this display, yes, can you place it now?
Yes.
Yes. Let's say the value is for the reference. This is even class rate. Value is 19.99 or 20. It is exactly 20.0002 or 3. Yes. So this value will become the first reference value, or you can change this value from test weight. Now take the test value, test weight. Yes, what is the value?
20.00002.
This is the test rate. Similarly, we will again repeat test and then reference. So this is the way how we can take the value of A, B, B, A per cycle, and then we can calculate delta M mean value, which is nothing but B1 minus A1, that is test weight minus reference weight, plus B2 minus A2 and divided by 2. We can find this mean value delta M. This is the way how we calculate this delta M for one observation, AB BA method. If we go for the complete cycle, it will resemble like this. This is the first cycle, ABBA. We have calculated delta M. If you take the 10 observations and readings, it will resemble like this. Serial number, observations, and delta Mi. This is A, reference, first value, B, best, first value, again test, and again reference. Serial number 1, which we have just calculated, that is 90.508, 20.4014, again 20.4016, and it is 20.000. And then we calculate this delta Mi, which we have already known about this. B1 minus B1 plus B2 minus B2 divided by 2 for calculating delta M. It becomes in micrograms, if you are taking, the value becomes 16. Similarly, second, third, fourth, 5, 6, 7, 8, 9, and 10. We used to take 10 observations and then we will calculate 10 means, delta Mi, 10 means. If we calculate the delta M, then we will calculate delta M of the last, the whole values. It will be the mean of our, it becomes, let's say, 15.3 microgram. 15.3 microgram, we calculate all the calculations. We'll share this sheet with you. You will find that all the calculation is being done. So this is the way for the calculation of measurement uncertainty of the weight. We are putting reference weight and then the test weight, and one by one we are just taking the observations. We have just taken AB, we have used ABBA method for the substitution method. We are finding the measurement uncertainty. For this measurement uncertainty, we have calculated that delta M bar, the mean value and the mean delta M bar is nothing, it is 15.3 milligram, sorry, microgram. This is the way how we have calculated. Now, what are the factors, other factors which will take part in the determination of uncertainty of the weight? I am rubbing it again. So till now we have calculated mean value delta M bar, which is
15.3 by 5. I'm sorry. I think you are not visible. The mean value bar is 15.3 micrometers. This is one value which we have calculated from the substitution method. Now, if you talk about other uncertainties which will take part due to the standard reference rate and the density of weight, etc., we find that, let's say, the standard rate which we have used is 20 gram. Its mass value of the reference weight, mass value we have taken from the certificate given by the National Physical Laboratory. We have the mass value of this weight. It is 90.999 and 985 plus minus 0.3 microgram. This is in grams. We have taken it from the certificate with K factor 2. If we talk about this is the value given from the certificate, the standard mass or the reference mass which we have calculated from National Physical Laboratory. Density of reference weight rho r is given as 7.950 plus minus 0.140 gram per centimeter cube, taking K equals to 2. If we calculate volume of reference weight, it becomes its mass value divided by its density. Its density is 20 divided by 7.950 gram per centimeter cube, which becomes 2.5157 centimeters. This is the way we have calculated the density, which is known as, and the volume of the reference weight mathematically. If you talk about the test state, density of the test state proteins 8.400 plus minus 0.170 gram per centimeter cube taken as equal to 2, and we can find the volume of test weight VD, can call it PR. VD is nothing, it is 2.3810 centimeters. So this is the way how we have calculated the density, and we have calculated the volume of reference weight and volume of test. Both are not known to us. And if we talk about the air volume, if the battery is not sitting, both are displaced cities can be replaced by -0, or otherwise we have to calculate the which is air by description. We call it GC. There is a volume of test weight minus volume of reference weight, density of air minus density of Q. No. When we calculate it becomes 0.000 6 of milligram, as we calculate, take this density, standard density 1.5 milligram per centimeter cube. We take this reference density not as 1.2 milligram per centimeter cube. Is it visible?
Yes, sir.
Visible? Somebody is saying it is no. Is it okay? You just check my mobile. Somebody was saying that there is no. Please check. I will just move this mic. Now, so this is the way we can find how much is the air bias correction, and after this air bias correction, what will be the conversion mass of that rate? I'm going to this. Conversion mass of test rate, and this nothing, it is MR plus air bias correction plus CR. And when we calculate the reference rate taken from the certificate was 90.99985. It is calculated 0.006 gram plus it has calculated 15.3 milligram, or we can say in grams it is 0.00015 in grams, and it becomes 20.006 gram. So this is the way we have calculated the conventional mass. The air concentration we have calculated time. We have calculated air concentration ATC, which was 0.006 milligram, and then we have calculated the conventional mass, and it is 20.0000006 gram. So this is the way we have calculated these three parameters for further calculation. Now, standard uncertainty due to weighing process. Now we are calculating the uncertainties. Uncertainty due to UA or type A and type B. First of all, standard uncertainty due to weighing process. Which we call type A UW. How we can calculate? Standard deviation S, which is nothing. It is square root of summation of I is equal to 1 to n. Delta m minus delta m to the square divided by n minus 1. We have to calculate delta mi minus delta m for all the values. Delta mi is individual mean values which we have calculated in the table, and delta m is the mean value which we have already calculated. So when we solve this, n minus 1, n is 10. We have taken 10 observations. Delta m is this. We have already calculated delta m, and delta m is the individual mean values of the 10 observations. V2 as A2 plus V1 minus A1 divided by 2 in all the 10 observations. When we calculate, it becomes 1.42 microgram, and standard uncertainty due to weight process due to the it is S acceleration divided by N. S we have calculated, N is equal to the other of that, and it becomes 0.45 micrograms. So this is a very standard uncertainty due to weight process such as uncertainty we are calculating which is 0.45 microgram. Very easy way how to calculate actually in this calculation we don't need more parameters, more factors. Only this ABB method for the calculation mean value is only required for the calculation of finding this standard uncertainty due to weight process or type A uncertainty. Now for finding type B uncertainty, I'm applying it. So UA we have calculated. Sorry, UW we have calculated directly as uncertainty. This is 0.45 microgram. UW and A uncertainty we have calculated. Now, next is standard uncertainty of reference rate. This will be used in directly. This is called UR. They have taken when we talk about this reference rate value, it's the reference rate value UR. Which they have taken from the study class 19.999 plus minus 0.000003 gram. This was the what is equals to 2. This was the value which we have taken from of this reference weight of the certificate of material, and shows that the rest of the is 3 microgram. So we can say that the value of this reference weight uncertainty of reference weight taken from the certificate is 3 microgram for kg is equal to 2. It is from the certificate. Therefore, standard uncertainty of reference weight UR is nothing, it is U divided by A, and simply it becomes 1.5 microgram. And when A is equals to the Standard. The first was 3 milligram. But when you call out the standard uncertainty, it becomes 1.5 microgram. Similarly, standard uncertainty due to drift in mass values between calibrations. Drift in mass values between calibrations. Due to drift in mass values between calibrations. Again. Fact like the uncertainty is called drift. Let's say it is a change. The value of this calculation of this drift value. Let's say some different value, and now let's say this is of 2 microgram. If drift is 2 microgram from previous data. Let's say we have done about some time back. We have done the value of this, and now when today it comes the variation in 2 microgram. Then uncertainty in due to drift will be uncertainty drift will be 25 by sorry. Drift value divided by square root of ED, which becomes 1.52 microgram. So this is the way we have calculated this guidance uncertainty, which comes to the APD value factor or changing in the observations of the balance. That was here. Then we have calculated standard uncertainty to the straight state. Then we have calculated and back when we do this reading. It is let's say 1.2 microgram. Now the next is I'm going to do now. So we can say this is A, then we have calculated UR, which is 1.55 microgram, and U2 ER is 1.5 microgram. These are the which we have calculated. This is type A, type B, type B. Reference rate, this value. इसके हम क्या रहे हैं? सबसे पहले जो बैलेंस शीट के अंदर अलग रेट करते हैं, सब्स्टिट्यूशन मेथड के मेथड से जैसे अपने कला इस सबकी वैल्यू निकाल करके अपने डेटा एम बाहर निकाला, निकाला, उसके बाद इसके बाद जो हमने की वजह से और दूसरी निकाली है की वजह से। अब इसके as far as because don't worry, हम लोग आपको में इसकी एक्सेप्शन को भी शेयर कर देंगे। देखने के बाद आज आप कर सकते हैं। लेकिन जो मेथड है उससे ये सब का प्रयास किया है बोले ताकि आपको पता चले क्या है इस सारी चीजें जो हमारे लोग को करते हैं उस समझने में समझ में आती है। साथ हम लोग actually we share for the considering calculation of mass and balance. You can immediately put the values, data, and can calculate it. As far as subdivision method is concerned, we will take one another session of 2 hours, maybe 2 hours, 4 hours, very soon, so that we can also calculate the uncertainty to subdivision method. or in subdivision method for calibrating even class weights with even class itself. Next type of uncertainty, which again take part in type B uncertainty, which is standard uncertainty of the air buoyancy. Standard uncertainty of the air buoyancy. This is again type B, and you call it free. We talk about it. To be better than uncertainty. Average temperature Celsius. Due to this temperature, the uncertainty is 0.3 for H equals to 2. So it will become 0.0 standard uncertainty. How we got it? The thermometer which we have got calibrated, thermometer must be some uncertainty related to the certificate of this uncertainty, which is given at equals to 2. We can find this is uncertainty and this is standard uncertainty. Similarly, for the relative humidity, in terms of percentage, 1.3 for K equals to 2. The relative uncertainty becomes 0.65. And then for pressure, in terms of millibar, again we have taken from the calibration certificate. Given we have get it calibrated from any of the, we generally get it calibrated from NPL only because our all instruments are calibrated from NPL. So we used to take the uncertainty, we used to take all the values from National Physical Laboratory certificates. The uncertainty, expanded uncertainty declared is this much, and when we calculate, this becomes the standard uncertainty is 0.06. So this is the way we have calculated, we have find all the values from the calibration certificates. All the values are known to us. Now, if we want to calculate the standard uncertainty of air density, it will become, I am rubbing it because all values are constant. All these three parameters are known to us. Standard uncertainty of air density it was air buoyancy correction. I'm sorry, correction word was left at the time. This standard uncertainty of the air buoyancy correction. Now, first of all, standard uncertainty of air density, it becomes U rho A is nothing which equals to rho A multiplied by square root of UF divided by rho A to the square plus U P over P square plus standard deviation, standard uncertainty of due to temperature, due to thermometer or temperature, UT by T square plus URH over 10 raised to the power 4 square. This UF is nothing. It is uncertainty in formula used, and it is nothing. It is 2 into 10 raised to the power minus 4 rho A. This is basically for approximation formula. So in this standard uncertainty of air density is nothing. U rho A is equal to rho A multiplied by UF above by rho A to the square, UP by P by square plus UT by T square plus URS by 10 to the power 4 square. When we put all these values which we have just calculated, it becomes the value is 0.00063 milligram per centimeter cube. The standard uncertainty of air density U rho A is nothing. It is 0.00063 milligram per centimeter cube. And if we talk about the standard uncertainty in density of reference weight, I have to just rub it because first of all they are calculated all these values UP, and URH. PT and rho are constant which are known to us. What was the temperature, pressure, and the relative humidity, which was all known to us. Rho A is also known to us. We have already calculated. So with the help of this, we can calculate. We can find the standard uncertainty of air density. Now, so we can say we have calculated first standard uncertainty of air density, which is 0.00063 gram per centimeter cube. We will use it shortly for finding the standard uncertainty of the air buoyancy correction UB. Now, standard uncertainty in density of reference weight U rho R is nothing. It is the expanded uncertainty of reference weight divided by K. It is 0.140 divided by 2. It becomes 0.070 gram per centimeter cube. This we have again taken for the certificate. What is the standard uncertainty in the density of the reference weight? When we calculated in the beginning, when I mentioned it, the density of the reference weight was 7.950 plus minus 0.140 grams per centimeter cube, taking coverage factor K 2. Now, when we are talking about this expanded uncertainty, it was 0.140, which we have already aware from the certificate given by the calibration laboratory. So, with the help of this, we have found what will be the standard uncertainty in the density of reference weight. It is also required when we will calculate for the buoyancy correction, uncertainty in the buoyancy correction. Now, next we require, so this is one part which we have calculated. Second is standard uncertainty in density of reference weight, which becomes 0.070 gram per centimeter cube. And the next parameter which we require is standard uncertainty in volume of reference weight. Standard uncertainty in volume of reference rate. Again, we are aware of volume. This is UVR is equals to U rho R divided by rho R into VR. U rho R we have already calculated, which is 0. This is the standard uncertainty in density of reference rate 0.070 or divided by density of the reference rate multiplied by the volume of the reference rate. Then because this U rho R we have just calculated standard uncertainty in the density of the reference rate. Density of the reference rate is known to us. Volume of the reference rate is known to us. When all these parameters are known to us, if we will put the value, it becomes, I'm just putting it again so that there should not be any confusion. 0.070 divided by 7.950 and multiplied by 2.5157. When you will calculate, it becomes 0.0222 centimeter cube. So this is the standard uncertainty in reference rate. This is, we have calculated the third value. Basically, we were requiring this standard uncertainty in volume of reference rate. Actually, we require for this calculation of uncertainty of air buoyancy correction, we need standard uncertainty in volume of reference rate, which become, I'm reading it, this much. This is the standard uncertainty volume of reference rate. How I calculated? I took this reference rate, volume, and this. With the help of this, we have simply calculated it. This becomes 0.0222 centimeter cube. In the similar way, similarly, standard uncertainty in volume of test plate. We have to again calculate in the similar manner as we have done it right now, which will become UVT, which is 0.0198. This is the standard uncertainty in volume of test weight. So basically, what we require is standard uncertainty in volume of reference rate, standard uncertainty in a similar way we will calculate first standard uncertainty density and then reference rate. Similarly, in terms for the test weight, we will again find the standard uncertainty in density of test weight. Similarly, as we did it in this formula, and we will again put it and get the standard uncertainty in volume of test weight. Now, standard uncertainty due to buoyancy correction, which we have to calculate from here. Standard uncertainty due to buoyancy correction. Now we can calculate U B. It is nothing. It is equals to square root of Vt minus Vr square multiplied by U rho A square plus UVT square plus UVR square into rho A minus rho naught square. All these values are known to us. When we will put all values, it will become 1.29 microgram. Standard uncertainty of air density, that is U, it is U rho A. This is known to us. VTBR we have calculated. We are very well aware volume of the test bed minus volume of the reference bed, and standard uncertainty in test bed, standard uncertainty in reference bed, density of air minus density at 0. So reference, which all known to us. So this is the way how we can calculate the standard uncertainty in due to buoyancy correction. This is again type P uncertainty. This is one another uncertainty which we have calculated. Now the next is, so I will say this standard uncertainty of the air buoyancy correction type B, it will become 1.29 microgram. Rest I am rubbing now because this is not required now, because all these values which we require for buoyancy correction we have taken. The next is standard uncertainty due to display resolution of the balance. It is again type P, or it will take part in the type P uncertainty, which is UBA. First of all, if we talk about the UT, it will become UB, it will become resolution D by 2 to 3 and multiplied by root 2. As this balance is of 6-digit balance, it has its least count 1 microgram. So it will D is resolution which is 1 microgram, and when we put all values, it will become 0.41 microgram. This is the standard uncertainty due to display resolution of the balance. Now, if we calculate combined standard uncertainty, you see, it is nothing, it is square root of UW square, which we have taken in the beginning, type A plus UBR plus UR plus UB plus UB square. All values we have calculated, and when we put all these values, it becomes 2.39 microgram. So this is the way how we calculate this value. If we talk about the yes, The next is effective degree of freedom. If we talk about the effective degree of freedom, new effective, it is nothing, it is n minus 1, n was 10, uc to the power 4 over uw to the power 4. This is the way how we can calculate this the new effective or the effective degree of freedom. When we calculate, it becomes 7193, which you take nearly equal to infinity. And for infinity, we can take the value as 2. If we talk about the effective degree of freedom, because now this is the combined uncertainty we have calculated. I'm just rubbing 2 or 3 lines. Phase 2. So this is the way how we can find the combined uncertainty in this calculation. If we talk about the uncertainty button, how will we prepare the uncertainty? This, I think it is somewhat not very difficult to calculate. However, we can calculate it with the help of these because it's a simple process. We have to follow the process and then we find that all the values are itself coming. uncertainty budget. Also, uncertainty, XI, estimates, limits, probability distribution, standard uncertainty, sensitivity coefficient, uncertainty contribution, and degree of freedom. XI, small xi, time, division, 2xi, pi, 2i, y, and so on. First is uncertainty of in weight was due to weighing process. Estimated was 1.42 microgram. Limit is again 1.42 microgram. Type A, normal. What is okay? Yes. So weighing process. Photo microgram. Your size is 0.45 microgram and division is so 0.5. Coefficient is 1. Is less than 0.45 microgram and equivalent is. And to do reference weight, it is 3 microgram. 3 microgram again. This is type B. Normal. 2, 1.5 microgram. In 1.5 microgram. Similarly, drift in reference weight, air buoyancy correction, resolution of balance, and then combined standard uncertainty. You see, coverage factor A and then expanded uncertainty. So this is the way how we can prepare this complete uncertainty. In this way, and we can calculate the values of this measurement uncertainty for a mass on the weight. So therefore, we can say the conventional mass value, which is because of the uncertainty is 5 microgram, so the conventional mass value of 20 gram weight will be 0.006 plus minus 0.00005 gram. When coverage factor K equals to 2. So this is the way how we can find the uncertainty of mass, uncertainty of weight in case of when we are calibrating through the substitution method or ABBA method. This is the way how the calibration or the weight can be done and the measurement can be calculated. So this is the way, it's a complete exercise, complete practice, by which by putting the value one by one, we can calculate the measurement uncertainty. Now, if we talk about the measurement uncertainty of a balance, because we have very short time, I will try to finish it within half an hour or maybe 20 minutes, so that then we can take the question answers. Now, measurement uncertainty of a balance. Let's say we are taking 1 kg balance. But volume is there now. What is low आवाज आना चाहिए ना आवाज आता है ना हेलो हेलो आ रहा है now measurement uncertainty of a balance. So how we can calculate the measurement uncertainty of a balance of, let's say, plasma balance of 1 kg. Let's say we are having a balance of 1 kg. Its maximum capacity is 1000 gram. Multiplication scale in terms of P value. Let's say it is 0.01 gram. The minimum capacity is, let's say, 0.2 gram. Linearity declared by manufacturer is 0.03 gram, and drifting balance indication is 2 ppm per degree Celsius. So this is these are the values which are known to us for a weight balance. It is 1 kg balance. Can you show the indicator? No, yes, good. So indicator can be, you have taken the 1 kilogram weight. Yes, sir. Reference weight, very good. And now this is visible to all, that the indications are visible to? Okay. So all these are values which are given by the manufacturer of this, and we are able to find these values. Now we are taking the environmental conditions at the same time. We are writing down the environmental conditions temperature. These are at start and at end. Temperature is, let's say, 23.3 degrees Celsius. It is in degrees Celsius. So don't put it again, right? 23.3. And at the end of the day, it is 23.2. Relative humidity percentage 50.6 and 50.3.4. Pressure in millibar from 979.5 to 979.4, and time is from 10 a.m. to 10:35 a.m. These are the values which are known to us in this measurement. What is the capability of this weighing balance, and what are the environmental conditions that we are going to calibrate a weighing balance? First of all, we will perform the weighing performance test. I am running it. Yes. Weighing performance test. The formula for calculating error is equals to I, that is indication, plus half E minus delta L minus L. I is the indication of the balance when we are putting any weight on the balance. This is error. This is indication. This is verification state interval known to us. This is additional load to reach to the next reading, and load placed on the weighing part, weighing balance. This is error, and the corrected error EC is equals to E minus E naught, where E naught is error calculated at 0 or near 0, which in this case we have calculated plus of 0.01 gram. The verification scale interval was 0.01 gram, and this is the verification scale interval, and this is the error which we have calculated at 0 or near 0. And it is used for calculating the corrected error, which is required to be calculated in the observation table. Now, if we take these readings, load, how much load L they are putting, how much is indication in gram, one when weight is up and when weight is down, when we are increasing the weight or when we are decreasing the weight. Additional load Delta L is again in gram. Again, when we are increasing the load, when we are decreasing the load. Similarly, error in gram when we are adding or decreasing. Corrected error is in gram decreasing, and the last is MP, maximum permissible error. We have a formula for calculating the maximum permissible error. It will be the maximum permissible error MPE will be either half E plus minus 1E plus minus or 1.5E plus minus. As per the load cell verification scale interval, calculating the scale intervals, we can calculate how much will be the maximum permissible error. I think we have discussed it in the morning, but I explained properly. Similarly, we will put all the loads starting from 200 milligram to 1000 gram. We will calculate the observation. Just put it 1 kg weight on this balance. Okay, how much is the reading? Okay, very good. So this is the way how we are calculating. We are taking the readings. Let's say it is 1000.04. Again, it is 1000 gram 0.04. Additional load is 0.005 gram, and this is 0.006 gram additional load. When we calculate error, it becomes plus 0.040, and another is 0.040 error. And when we calculate the corrected error, it becomes 030 and again 030. The error is, the maximum permissible error is 0.515, let's say gram. The error allowed is 0.015 gram. However, the calculated error is, the corrected error is 0.03, 0.03. So machine is not passed, machine is failed. However, when we are going to calculate the measurement uncertainty, we will actually calculate, we will not find this whether it is passed or failed. We will calculate the measurement uncertainty, how much is the uncertainty in this calculation. So this is the way which is the weight performance test. Actually, in weight performance test, what we observe that all the laboratories are now doing the weight performance test in such a way they are just putting what they are doing, they are just putting the load, taking the indication, and finding the error between load and the indication. In most of the 99% of the laboratories are doing the finding their errors in this way. But the actual way of finding the error is this: we have to calculate indicate, we have to see load, indication, then additional load, then error, then corrected error, and then we got the additional load. Additional load is, let's say, we can just explain you. Suppose when we are putting this weight, it becomes 1000.04. Then how much additional load we have to place on the pan to take it up to the next reading, that is 1000.05. So that load is called the delta L. To take it to the next observation, next reading, that is called delta L. Then we will calculate error, corrected error, and the maximum permissible error. So this is the way how a weighing balance has to be calibrated with the for the uncertainty calculation. Next is eccentricity. Similarly, we will do the eccentricity test. That first of all, and all the corners we will take at the center. Then first, can you show? I'm not. ये इसकी आपकी पूरी भाग रही है, नहीं कर पा रहा, देख पा रहा। चलिए नहीं, आप फिर से आप कैसे बोलो? Now, see, this is one test. I'm just coming it out. This is weighing performance test. In weighing performance test, the error is not actually load minus indication, but it has to be calculated with a given formula, which we are not doing actually, and it is all wrong. सर क्वेश्चन आंसर लेने क्या करें जब और इसको फिनिश कर दो सर eccentricity test, which we also called corner test. It's a, I think, rectangular balance. Is circular or rectangular? Rectangular. So in this case of rectangular balance, this is center. We connect position 1, 2, 3, 4, and 5. This is the whole distance, and we will place here, then here, in between these two, in between the positions like this. We'll place the weights like this. And in a similar way, we'll find the eccentricity test, the formula for the error, same as we have done. Corrected error is also same as we have done in case of performance test. Let this eccentricity test has to be taken at 1/3 of the maximum capacity. As it is a balance of 1 kg, we are taking it at approximately 300 gram or 350 gram, whatever it is. We can take either 300 gram or 350 gram. Now again the table in the similar way as we did for the performance test. Load, location, indication, additional load, delta L, error E, corrected error EC, and MP. For this balance, it will be 0.015. Let's say the location is 1, load is 100 gram, indication is 100.02. For taking the next reading, it is 0.003. Error becomes 0.022 and corrected error is 0.012. All are in gram. So this is the way how we can find the corrected error and the for observation 1. Similarly, location 1, 2, 3, 4, 5. Again, 1, 5, 4, 3, 2, 1. So this is the way how we can calculate. You can take the two observations 1, 2, 3, 4, 5. 1, 5, 4, 3, 2, 1. So this is the way clockwise and anti-clockwise. And in the morning, Mandal Sahib has told clockwise and anti-clockwise. We will take the observations and we will find that how much is the corrected error we have found. Whether it is within range or not, within limit or not, pass or fail will be decided by within the limit or outside of the limit. So with this corrected error, we have all these corrected errors with the time value. Then we can find the mean corrected value. Corrected value and mean corrected error. It is taking with location 1, 3 values, x1 plus x2 plus x3 by 3, location 2, location 3, location 4, and location 5. So you will get the values at location 1 it is 0.004, location 2 0.026, 0.0025, 0.025, and 0.025. So these are the values which we have calculated at different points. Locations 1, 2, 3, 4, and 5. Now, if we take it the deviation from the center is position 1. Deviation from center, that is position 1. It will be for location 2. Location 2 is 0.026 and location 1 is 0.004. So it becomes 0.022. Location 3, it becomes minus 0.0015. Location 4, it becomes 0.021 in grams. Location 5, it becomes 0.021 gram. So this is the way we have found these are the deviations from the center position, and it is a maximum deviation 0.022 gram, which we will take for uncertainty calculation. This is the second test, which is the eccentricity test. We have taken the 1/3 of the load, we have taken the 1/3 of the load, locations 1, 2, 3, 4, 5, 1 again 5, 4, 3, 2, 1. Indication, additional load, error, maximum permissible error, which we are known to us, and this maximum permissible error is to just pass or fail the balance when it is required under the legal methodology. If you are calculating the uncertainty calculation, it is not required to pass or fail. Then we have found the mean corrected error at different locations, location 1, location 2, location 3, from these observations, corrected errors. And then we have found the deviation from the center position, position 1 of all these locations. Out of all these locations, the maximum value will be taken as will be considered for calculating the uncertainty. And the last is the repeatability test. The last test is repeatability test for calculation of uncertainty in measurement of balance. Repeatability test has to be taken at two loads. One is half load and another is full load. For this half load, we have to calculate P, which is I plus RP minus L delta L. Similarly, at full load, again the same formula, RP minus delta L. We will take 10 observations for both of these two. It is number of observation, indication, because it is half load. Half load is 500 gram and full load is 1 kg 1000 gram. Half load, this is indication, then delta L, and then P. One observation, let's say 500.01 gram, delta L required is 0.004 gram, and when we calculate P, it becomes 500.011. Similarly, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We can take 10 observations and we can find the maximum value of this P, which is 500.011 and 500.021, and one value is 499.990. It is minimum value and it is maximum value. So P max minus P min, when we calculate, it is 0.031 gram, and maximum permissible error is 0.015 gram, which is less than the P max minus P min. So balance will fail, but anyway, it is not required in this case. Similarly, we'll do the same formula for full load, and again we'll take the 10 readings P max minus P min, and the MP we will calculate in the same way, and we'll find that how much is the value. With this all P, we will also calculate the mean value delta MR, which is for the calculation of uncertainty. Now, how to calculate the uncertainty? Because these are the three observations which we have to take. Again, in the same way, we'll do standard uncertainty due to weighing process, type A uncertainty, as we did last time. Delta MI minus delta M bar, This is for this weighing process, or the we can say for the repeatability. If we are talking that we are calculating the repeatability, this uncertainty at 1 kg, we will take this value. For 500 gram, this value, or at any weight, we can find that we can do the repeatability test and we can find what will be the uncertainty coverage for that particular weight or at that particular load. This is mean value. All these are mean values. This is delta M. We can calculate delta M, and then we can also calculate all individual delta M's. And by putting the value as we have done already in case of weight, we can find the uncertainty, type A uncertainty. Similarly, standard uncertainty due to the reference standard, which we have already calculated in the last case. Balanced drift, we have already calculated. Display of resolution, which we have calculated. Due to drift in sensitivity, yes, due to drift in sensitivity, as we are aware, this is given by the manufacturer. Accordingly, we can do. And standard uncertainty due to eccentricity loading, we can also find it. How much is the eccentricity loading? Linearity, we have already calculated. Linearity divided by square root of 3, which is again from the table for performance test or the linearity test. And the combined uncertainty will be the sum of square root of sum of all these uncertainties. So this is the way how we can calculate in the similar way as we have done in case of weight. In the similar way, we can calculate on the uncertainty of the balance. So I think this is more than enough. We have to take some of the questions. मतलब सब ऐसा करते हैं, थोड़ी questions लेते हैं. Then we will continue for the, because again यदि मैं सारी answers बाहर निकालूंगा, it will again take half an hour. And in the similar way as we have done in the mass, because mass we have explained in a proper way. Or otherwise, in the next batch, whenever the next time will come, we will do for the balance again. So these are the basic ways how we can calculate the mathematical uncertainties. Now we are taking some of the questions because lot of questions were I have seen on the platform. We just discussed. Yes. Question number 1. In the beginning, not audible, not audible.
What is sensitivity coefficient? Usually this is 1 in case of mass and balance, because sensitivity coefficient is used only to convert the unit from one unit to other unit. Like in case of volume, sensitivity coefficient will be different. But in this case, mass and balance, it is always 1, because we are input quantity and the output unit basically both are same.
Either we are taking it in terms of milligram, microgram, gram or kg. So that's why in case of balance or weight, when we are doing the calibration of weight or balance, it will be the 1.
For example, in case of volume, basically we are taking weight from the balance, but finally we are converting into milliliter or microliter or liter. So we are converting from gram to ml. Like that, in that case, sensitivity coefficient will be different. Distribution. I think this is already explained in the uncertainty budget. This is probability distribution.
Okay.
This is already covered.
What we can do, we can just put a para on this probability distribution, because they are asking that which type of distribution we are talking, normal or this rectangular distribution. So what is normal distribution? What is rectangular distribution? I think we can put a para.
Actually, when any value is taken from the certificate, so this is called the normal distribution. or triangular distribution is basically when we know basically in this case of rectangular distribution, when all this only upper limit and lower limit is known, because we are taking the only few data. We are not taking 500 or 1000 data. We are taking only 2 or 3 data. So basically that's why we know the limit, upper limit and lower limit. So usually this is that's why it is taken as rectangular distribution in this case. Otherwise, actually, further distribution in future we can take another this session.
Or we can when we are
for the general
yes
uncertainty calculation.
Or what we can do at this time also, we can circulate what a basic para on all type of distributions, so that this will be clear. Very good question. Very good question. Does balance means any weighing instrument?
Yeah. Yes.
Balance basically, obviously, either two pan balance or now it is single pan balance. Balance maybe any type of weighing instrument, including the spring balance, hanging type balance, all type of balances are the same type of balance, but obviously within their uncertainty limit. Yeah, PPT will be shared shortly. GTCs allowed enable labs to be able to verify. GATC is allowing enable labs to be able to verify weighing instrument up to class 3. It's a different type of question. GATC will be taken off by the ministry. Even class weights calibration, any specific criteria is there for resolution of weighing scale? Yes.
Yes. Actually, this basically you have to calculate the uncertainty first. Because already this is this uncertainty limit is known from the YML R111, and accordingly, actually, what we do when we purchase the weighing instrument, basically we do the back calculation.
Yes.
Because few parameters are already known. For example, which standard we will be using, the uncertainty of that standard is known. If we purchasing the weighing balance, suppose resolution of the balance is 1 microgram, so we can calculate the uncertainty factor of that
display.
In case of E1 class, definitely we will be using the stainless steel weight, so buoyancy correction will be almost 0. So like that, so we can do some homework for the selection of the weighing balance.
Linearity and performance is the same test. For a weighing balance, for how many weights up to capacity, uncertain value needed to be provided. How many weights up to capacity?
Balance, how many weights up to capacity? Uncertain value need to be
It's maximum value.
Usually, how many weights means, if I understand correctly, you're talking about the number of loads. So usually this is 10 as per YML R76.
Or up to the weights, we can take up to the maximum capacity. Yes, last time presentations we will send today. I'll send. Yes, this presentation also by WhatsApp or mail. Actually, mail IDs we don't have. We have simply, it is difficult to send the mail, but anyway, we'll try our best. How to calibrate non-standard weight? How to define accuracy class? Non-standard weight.
Non-standard weight, actually, we cannot classify according to the standard, because this is not allowed as per YML R111. So only actually here I have not, this is due to shortage of time, I'm not able to cover all these things. Even not only mass value and the uncertainty is only criteria to classify this E1 class or E2 class. There are various other requirements as well.
Yes.
Construction of the weight, material of the weights, density,
susceptibility.
Susceptibility. So the various other criteria. So in future, we can do another.
Even class weight, I think we need one complete day for even class weight.
Yes.
Then only we can understand.
Merely just value and the uncertainty is not the criteria only.
Link, please. When a stamping certificate is provided, it means a calibration certificate only, but uncertainty values are not provided. Stamping is basically, he's talking about the verification certificate. Under the verification certificate of the legal metrology, we only declare pass and fail. We don't give the calibration. It's not a calibration certificate. But when a laboratory issues a calibration certificate, it gives its mass value as well as uncertainty related to it, or simply it gives the maximum uncertainty as per the OML R111. Which software is available for
uncertainty?
So actually, these are not software. Basically, we should say these are the Excel sheets, Excel calculations are prepared. We can share with all whatsoever are available. Okay.
Actually, in case of balance is concerned, repeatability is more important compared to others because if periodically, suppose quarterly or half yearly, you can check the repeatability. If repeatability is meeting your requirement within the specific criteria means suppose you have set certain value to meet your requirements, so that is sufficient, and you can maintain the data.
Yes. So basically, repeatability test has to be done in place of eccentricity check. Passing criteria for replicate, retain, intermediate test for test weight and balance.
Actually, usually this is the uncertainty limit.
Yes.
Suppose if our uncertainty limit is 3 micrograms, say, so our measured value should not be beyond the 3 microgram. Suppose you are, as I said, in case of, for example, periodicity also. If you are issuing the certificate with 2 years validity, so our mass value should not go beyond the 3 microgram.
Yes.
If our uncertainty with 3 microgram, if it is beyond the 3 microgram, that means our validity should be reduced. Yes. From 2 years to 1 year or even 6 months. So depending, so basically criteria is uncertainty, reported uncertainty.
What artifact should be used for intermediate check for even class weight?
Should be used intermediate. Actually, U1 class, because according to R111, U1 is the highest accuracy class. So few NMIs are using E0 class, but officially, as per standard, E1 class is used for the calibration of E1 class. Still, standard allows. Eccentricity. I think already you have repeated eccentricity test.
अगर हम रिपीटेबिलिटी का 10 रीडिंग देते हैं तो क्या एसेंट्रिसिटी के फैक्टर उसे करना जरूरी है?
No, actually, this is depending on the parameter. Parameter means in that case, in case of weight calibration is concerned. So in that case, eccentricity is already covered in the repeatability. Reason is that suppose I am not able to place the weight every time at the same location or at the center. Suppose 1 or 2 mm off centric is there. So what will happen? Reading will change. Ultimately, it will affect the type A uncertainty. Standard deviation will change, and finally the type A uncertainty. But in case of balance is concerned, when we are taking the direct observation, in that case we should do the eccentricity test separately. So this is basically case to case basis. Which tell us how value non-standard weight, but to
Same
MP.
Same है.
नहीं उसमें एक क्वेश्चन नॉन स्टैंडर्ड का
वो भी था सेम जो
ऑलरेडी हमने
any specific criteria for calibration of baby in balance in hospital?
Specific calibration of baby weight balance in hospital. The same criteria is covered. Is eccentricity test, we take weight range 1/3. Usually is 1/3.
Slide.
Capacity of the balance. Minimum capacity of the balance. This is
it is given as per the rules. It is as per the standard. It is given in the rule in the standard that for this class 3 instruments, it will be 20 times of its E value. For class 2 instrument, it will be either 20 times or 50 times of the instruments. So this is the way of how we calculate. It is as per the standard.
It's already given in the R76.
Yeah. But we will still do it in the next time. Okay.
Already we have covered.
Session, we can also check if there is a question. We can please. There are no more questions, right? Your discussion. Can we get this position? Yes. For even class of weights also, can we use the same procedure ABB or different? Yes, we can use ABB method if the uncertainty is good.
Method, but method will be different. There should be subdivision method.
No, ABB method, na?
ABB weighing cycle basically.
Makes sense.
ABB is not a method. ABB is a cycle. Method is subdivision.
No, can we use substitution method in this even class weight?
Actually, we can use this is not mandatory as per standard, but this is depending on the
Uncertainty of the weights.
But in case of sometime we are bound to follow the criteria of the accreditation body also. Like NABL has decided for the U1 class, you have to follow the subdivision method. So definitely we should follow the criteria of the accreditation body as well. But otherwise, as according to standard YML article, you can use the substitution method also if you are able to meeting the requirements of the standard.
If both materials same, we will into class. Voice is not, yes, voice is not there.
Actually, also this is depending on the density of the material.
Yes.
It is not necessary all the stainless steel weight will be density of 7950 kg per cubic meter. If suppose density of the standard is 8000 kg per cubic meter and density of the test weight is 7950. So in that case, you have to apply the ARYC correction.
Yes, subdivision method training will be provided by us. Very soon we will do this subdivision method, how we can do this. So with this, I would like to thank all the panelists, include especially Dr. Gautam Mandal, who has done, yes, share, we will certainly share the Excel sheets for the calculation. Dr. Gautam Mandal, who has explained this complicated topic, complicated subject in a very easy manner. Thank you very much, sir. We will take your help continuously. Our beloved director, Dr. Mr. B.N. Dixit, sir, who has taken his time from his busy schedule, even on Saturday. I know that due to some official contingencies, he is in the office, and director NPL, who was also in the office. So, you know, all the people are taking their time from their busy schedule. I'm thankful to all who have joined, who have simply motivated us for doing these type of programs. Thank you very much all. We will issue these certificates very soon, maybe by the next week. Everybody will get the certificates. The last training program certificates have already been issued and sent to all the emails. If there is any problem in any of the certificate to any of the person, kindly let me know. Thank you very much. All the best. We'll meet very soon next week. Thank you. Bye.